that we imported in from Hardhat. We're going to choose next. We're going to choose connect. And remember, for our front end bit, we're going to go to settings, advanced, reset account if we're working with a brand new Hardhat blockchain. Now, the front end doesn't look super nice, but we have an enter raffle button and we have a little bit of UI talking about the current number of players and then the most previous winner of our raffle. So we can go ahead and enter the raffle and allow anybody to pay 0.1 ETH to enter our smart contract. We get a little transaction saying transaction complete, and we get the current number of players is 1. We can continue to enter the raffle and anybody can enter this raffle, and the smart contract will keep track of all of the players in here. We're going to run this on a timer. The lottery is going to automatically trigger somebody to win. And to do this, to get a pure verifiably random number, we're going to be using Chainlink VRF to get a pure verifiably random number. And then we're going to use Chainlink keepers to trigger the automation to automatically have one of these winners get picked every time one of those time intervals is up. Once the keepers kick it off, they will pick a winner. Our decentralized lottery will say the most previous winner is so-and-so, and they will get all the money from this lottery, making a perfectly fair decentralized lottery. We're going to call our contract raffle.sol, but you can call it lottery.sol or really whatever you want. And we're going to make it look really, really nice. So now we're back in our Visual Studio Code. This is going to be the project. If you learn this, you have the skills to learn all the rest of these smart contract concepts, and you are going to be able to do great things in this space. This is going to be your flagship project. This is going to be the one that you can be the most excited and the most proud about for this tutorial. So let's go ahead and let's create a new folder. So we're going to do mkdir, Hardhat, smart contract lottery, FCC, or smart contract raffle, whatever you want to call it. Then we're going to cd into our Hardhat, smart contract lottery free code camp, and we're going to type code, period, or we're going to open this up in a new folder, however we choose to do so. Now that we're in our new folder, we're going to create our new Hardhat project. So we're going to do yarn add --dev Hardhat. And we'll get our node modules, our package.json, and our yarn.lock. Now we'll do yarn Hardhat to get started with a new project. And we're just going to select create an empty hardhat.config.js because we know what a basic project looks like. And we're going to give this project the customizations that we want to see. We're going to create an empty hardhat.config. And now in here, we have a blank hardhat.config.js with almost nothing in here. So we're starting completely from scratch. Now we're going to add all of our dependencies in here. And oftentimes you'll add these sequentially as you build, but we're just going to add them all in one line. And there are a lot of them. So we've left a copy pastable section of the full blockchain Solidity course.js for you to just copy paste so you can install everything in one go. So grab that line and it's going to have everything that we've been talking about. And we'll just hit enter and we'll install all of these. And as you create more and more projects, you'll get the feel of what you like for your dependencies and what tools that you like to use. Remember, at the end of the day, the tool that's best for you and best for the job is the tool that you like the most. There never really is a one tool fits all. There's almost always going to be trade-offs. All right, now that we have all those dependencies installed, if we look at our package.json, we'll have this massive dev dependencies. We'll have everything in node modules. We'll have everything in yarn.lock. And of course, as we know, in order for any of these to actually work, we need to add them into our Hardhat config. Now, there's a lot of stuff to add in here as well. So like once again, if you want to come to the Hardhat Smart Contract Lottery FCC and go to the Hardhat config, you can just copy paste everything and place it into your project so that you don't have to always type everything out yourself. Nomic Labs, Hardhat Waffle, Nomic Labs, Hardhat Etherscan, Hardhat Deploy, Solidity Coverage, Hardhat Gas Reporter, Hardhat Contract Sizer, which we haven't talked about yet, but we will, don't worry, and then require.env.config. And as you all know, all these little semicolons are popping up, and those are going to drive me absolutely crazy. So once again, we can create a dot prettier RC. And if you want to copy this as well from one of your previous projects, feel free to do so. One thing that I added in here was a print width of 100. This just changes how long a line can be before it goes onto a new line. That's the only difference here. Now, if we go to our config and hit save, they go away. Thank goodness. Now, if we look at our Solidity version, we're currently using 0.7.3. Let's go ahead and update that to 8.8 or 8.7 or whatever you want to use. Now that we have all the basics set up, we can begin coding our smart contracts. So we first need to create a new folder called contracts, where we're going to store all of our contracts. And let's go ahead and create a new file called lottery.sol or raffle.sol or whatever you want to call it. I'm going to call mine raffle.sol. And you might see this indexing thing happen from time to time. It's our Hardhat Solidity extension indexing all of our node modules so it knows how to highlight things and knows how to work with everything in our Solidity files. So that's what happens when that pops up. Now, before we jump in and create it, let's figure out what we're going to do. So we're going to create our raffle contract. And what do we want people able to do? Well, we probably want people to be able to enter the lottery, paying some amount. We're probably going to want to be able to pick a random winner. But we want this to be verifiably random. We want this to be untamper-withable. And we also want winner to be selected every X minutes or years or months, AKA we want this to be completely automated. So we want to deploy the smart contract and almost have no maintenance, almost have nobody ever have to touch it again, and it'll just automatically run forever. This is the power of smart contracts. As we know, since we're picking a random number and we have some event-driven execution, we know that we're going to need to use a chain-link oracle, since we're going to need to get the randomness from outside the blockchain, and we're going to need to have that automated execution because a smart contract can't execute itself. We need somebody to automatically trigger these. So to trigger selecting a winner, we're going to have to use the chain-link keepers. And that's pretty much going to be our entire code. Now, I usually like to do this before I start any project. And the reason that I do a little bit of brainstorming is because we don't want to just jump in and really do anything. We want to have a good idea of what we're trying to build so that we can write tests for it, so that we can know if we're going in the right direction, etc. Now that we have a good idea of where we're going, let's build it. So, per usual, let's do spdx, license identifier, MIT. We'll do pragma, solidity, little caret here, 0.8.7. I'll even zoom out just a hair. We'll trash that. We'll say contract, raffle. We can even make sure that we're not going crazy by doing a little yarn, hardhat compile, and compiled successfully. We want it to be able to enter the lottery. We want users to be able to enter it. So maybe we'll create a function called enter raffle. What else do we want to do? We want to be able to pick a random winner. So maybe we'll create a function called pick random winner. And boom. So let's comment out pick random winner for now, and let's just work on this enter raffle thing. In the past, we've created projects like FundMe where people can send Ether to our contracts or send whatever native blockchain token to our smart contracts using the message.value based off of some USD value. For this one, we're just going to have the entrance fee instead be USD based. It's just going to be that native asset. So for our enter raffle, we don't have to set a USD price. We can just set a minimum ETH price. So up at the top, let's pick our minimum price. So we'll do a UNT256 entrance fee. And now some of our learnings from our last section should come in here. We now know that this entrance fee is going to be a what? It's going to be a storage variable. So let's prepend it with s underscore. Let's make it a private variable because we always want to set our visibility, but let's have the entrance fee be configurable. Well, let's create a constructor now, and we'll have this entrance fee be settable in our constructor. So our constructor will take a uint256 entrance fee, s underscore entrance fee equals entrance fee. Well, if we're going to only set this one time, we might as well make this a constant or an immutable variable. So let's make this an immutable variable so that we save some gas. We'll change this from S to I, and now we're saying uint256 private immutable I entrance fee equals entrance fee. Now we probably are going to want other users to see the entrance fee. So down below, we can create function get entrance fee, and this will be a public view function, which will returns a uint256, and we'll just say return I entrance fee. Now we have a function that users can call to get the entrance fee, but we as developers can use this I entrance fee to know, this is an immutable variable. This is pretty cheap gas-wise for us to read from. In our enter raffle, we've done a ton of these before. All we need to do is we just need to require the message.value is greater than that I underscore entrance fee. But we've learned before about those error codes. So we could use require message.value, or we could do one of these custom errors, which is going to be a lot more gas efficient, because instead of storing this string, we're just going to store an error code in our smart contract. So let's do that instead. We'll say if the message.value is less than our I entrance fee, then we're just going to revert the whole transaction with some error code. And we'll use our best practice naming raffle underscore underscore, not enough ETH entered. And we'll grab this arrow code and we'll have, if the user doesn't send enough value, we'll revert with not enough ETH entered. Now that we know they're calling enter raffle with enough value, we're probably going to want to keep track of all the users who actually enter our raffle. That way, when we pick a winner, we know who's in the running. So let's create an array of players at the top. Error here. And then just to make this look even nicer, we'll do a little comment here and we'll say state variables. And we'll combine both our storage and our not storage variables just in this state variables section. So we'll do address array players. Now players, of course, is going to have to be in storage because we're going to modify this a lot. We're going to be adding and subtracting players all the time. So we're going to do s players. We'll make this private as well. And we're going to make this address payable players, because if one of these players wins, we're going to need to have to pay them. So we'll make this address payable private s players. And since we're going to make this private, and it's probably good that we know who's in the players array, we'll even do function get player. This will be a public view that returns an address of one of these players, and we'll just return s players of index. We'll have this function take a uint256 index as an input parameter. We know that players is going to be a storage variable, and we're going to add it to our enter raffle. Oh, and we definitely want our enter raffle to be public and to be payable, since we're having people send message.value, and we want anyone to be able to enter our raffle. So it'll be public, it'll be payable, it'll be perfect. Now that we have our array and someone's entered the raffle, we'll do s players dot push message dot sender. Now this doesn't actually work because message dot sender isn't a payable address, so we'll need to typecast it as a payable address just by wrapping it in payable. So now we have a way to keep track of all the players that are entering our raffle. Now, one of the concepts that we haven't gone over yet is actually going to be events. And events are really important to our smart contracts. Whenever we update a dynamic object like an array or a mapping, we always want to emit an event. When we get to lesson 10, and then especially lesson 15 with the Next.js NFT marketplace, these events will make a ton of sense, especially for front-end developers. So right now, events might be a little bit of a weird thing for you as we explain it, but as we continue on, they'll start to make more and more sense. So we're going to start adding events to our smart contracts whenever we update one of these dynamically sized data structures. And to learn more about events and how to use them, we're going to watch another video that explains all about events. You can absolutely follow along with this video as a side project, but let's learn all about events.
Now, if you've worked with Solidity, you've probably seen these things called events before. Or maybe you haven't seen something like events, but you've always wondered how Chainlink or the Graph or some of these other off-chain protocols work under the hood. And in this video, we're going to learn about logging and events in Solidity, viewing those events on Etherscan, and then working with them in Hardhat. Now, it's the Ethereum Virtual Machine, or EVM, that makes a lot of these blockchains tick, like Ethereum. And the EVM has this functionality called a logging functionality. When things happen on a blockchain, the EVM writes these things to a specific data structure called its log. We can actually read these logs from our blockchain nodes that we run. In fact, if you run a node or you connect to a node, you can make a getLogs call to get the logs. Now, inside these logs is an important piece of logging called events. And this is the main piece that we're going to be talking about today. Events allow you to print information to this logging structure in a way that's more gas efficient than actually saving it to something like a storage variable. These events and logs live in this special data structure that isn't accessible to smart contracts. That's why it's cheaper, because smart contracts can't access them. So that's the trade-off here. We can still print some information that's important to us without having to save it in a storage variable, which is going to take up much more gas. Each one of these events is tied to the smart contract or account address that emitted this event in these transactions. Listening for these events is incredibly helpful. Let's say, for example, you want to do something every time somebody calls a transfer function. Instead of always reading all the variables and looking for some to flip and switch, all you have to do is say, listen for event. So a transaction happened, an event is emitted, and we can listen for these events. This is how a lot of off-chain infrastructure works. When you're on a website and that website reloads when a transaction completes, it actually was listening for that transaction to finish, listening for that event to be emitted so that it could reload or it could do something else. It's incredibly important for front ends. It's also incredibly important for things like chain link and the graph. In the chain link network, a chain link node is actually listening for request data events for it to get a random number, make an API call, or etc. Sometimes there are way too many events and you need to index them in a way that makes sense so that you can query all these events that happen at a later date. The graph listens for these events and stores them in the graph so that they're easy to query later on. So events are incredibly powerful and they have a wide range of uses. They're also good for testing and some other stuff, but you get the picture. They're really sick. Now that we know what events are, let's look at what they look like, how we can use them, and how we might use them in our smart contract development suite. Now, here's what an event is going to look like. We have an event here called stored number. So we have basically a new type of event called stored number. We're saying, hey, Solidity, hey, smart contract, we have this new event thing. We're going to be emitting things of typed stored number in the future. When we emit this event, it's going to have these 4 parameters. It's going to have a uint256 for called old number, a uint256 called new number, a uint256 called added number, and an address called sender. Now, for the astute people here, you might have noticed that there is another keyword in here, the indexed keyword, and this is a really important keyword. When we emit one of these events, there are 2 kinds of parameters. There are the indexed parameters and the non-indexed parameters. You can have up to 3 indexed parameters, and they're also known as topics. So if you see a topic, you know that that's going to be an indexed parameter. Indexed parameters are parameters that are much easier to search for and much easier to query than the non-indexed parameters. In fact, way back in that fgetLogs function, it even has a parameter allowing us to search for specific topics. So it's much more searchable than the non-indexed ones. The non-indexed ones are harder to search because they get ABI encoded and you have to know the ABI in order to decode them. Now this just told our smart contract that there is a new type of stored number, a new kind of event here. We need to actually emit that event in order to store that data into the logging data structure of the EVM. To do that, we need to do something that looks like this. This is what it looks like when we emit an event. It looks very similar to calling a function. So you call emit and then the name of the event, and then you add all the parameters in there that you like. Here's the full example of a smart contract that has an event and is going to be the example that we walk through in Hardhat. Now in this smart contract, whenever anybody calls the store function, we're going to emit this event. Here's an example of a transaction where we called the store function with a value of 1. Let's look into the logs to see what this event actually is going to look like. An event is going to be broken down like so. The address of the contract or account the event is emitted from. The topics are the index parameters of the event. Data. This is the ABI encoded non-indexed parameters of the event. What does this mean? This means that we took those parameters that were non-indexed, we matched them together with their ABI or application binary interface, pumped them through an encoding algorithm, and boom, this is what we got. If you have the ABI, they're very easy to decode. If you don't have the ABI, they are very hard to decode. These non-indexed parameters cost less gas to pump into the logs. Now in this particular contract, since we have verified the code, we verified the contract, Etherscan knows what the ABI is, and we can view this in dec or decoded mode. Hex mode is obviously the non-decoded mode, or in its raw hex or hexadecimal or encoded mode. You can read more about the layout of these events in the Solidity docs.
Now, so that's the basic introduction of events. And for those of you who want to watch the rest of that video and who want to actually practice using events yourself, there's a link to these videos and the code repository associated with that video if you want to play with it and if you want to learn more. So feel free to refer back to the full Blockchain Solidity course.js if you want to go deeper into events. Now that we're back and we've learned a little bit more about events, let's add some events to this contract. Remember, these events get emitted to a data storage outside of this smart contract. Let's create an event called raffle enter. A good syntax for naming events, name events with the function name reversed. So for enter raffle, we're going to say raffle entered. So up at the top, below our state variables, but above our constructor, we'll create a new section called events, and we'll create our first event. So we'll do event, raffle enter, and we'll just have this raffle enter take one index parameter. It'll be an address indexed player. So in our enter raffle, we're going to say emit raffle enter, and we're just going to pass it message.sender. I'm going to remove these comments for now, but feel free to leave them in as you code along. Now, in this part of my raffle coding or my lottery coding process, I probably would start already writing some tests and already writing some deploy scripts. The reason that we do this is it's good to test our functionality as we progress. And oftentimes when I'm writing smart contracts, I'm constantly flipping back and forth between my deploy scripts, my contracts, and my tests to make sure everything is doing exactly what I want it to do. For the purpose of this course, and just to make it easy for you to learn and follow along, we're not going to do that. And we're just going to keep writing their smart contract almost to complete and then move to our deploy scripts and tests. So in its minimalistic sense, we essentially have a way for people to enter our raffle. Now we need a way to pick the random winner. And this is where we're going to need Chainlink VRF and Chainlink Keepers. So let's again watch some sub lessons about learning about Chainlink VRF and learning about Chainlink Keepers. We've made some videos about these before, so we're just going to play these videos so you can learn about how Chainlink VRF version 2 works and also how Chainlink Keepers works. Then we're going to come back and we're going to add them into our contracts here. If you're already familiar and you already played with them, feel free to skip those sections and we'll just get to building them here.
Hi, my name is Stephen Fluin, and today we're going to be taking a look at Chainlink's VRF version 2. VRF version 2 has a few different mental models that we should be aware of, and I want to show you what it feels like to be using it. The big important thing to know about VRF version 2 is that instead of the VRF 1 model where you'd be funding your contract with Link, instead you're going to be funding a subscription, which is basically an account that allows you to fund and maintain balance for multiple consumer contracts. Let's dive into the docs and see what using VRF v2 looks and feels like. In order to show this off a little bit, I'm going to dive right into the get a random number guide in the Chainlink documentation. And so it's going to go through a few of the requirements of some of the technology we're going to use today. And the first thing it's going to ask us to do is to make sure that we are on the Rinkeby testnet. So let's go ahead and jump over to Rinkeby, make sure my MetaMask is unlocked here. And now that I'm on Rinkeby, great. I should be able to use the VRF version 2 testnet. Now we're going to jump over to Subscription Manager. And the Subscription Manager is where we're going to manage our subscription account. Basically, this is the place that you put the funds in order to be able to use it across a bunch of different chains. So we're going to go ahead and connect our wallet here in order to use the subscription app. And then we're going to go ahead and create a new subscription. So we'll just use my address as the subscription address here. I'll approve the creation. And as soon as that transaction is confirmed, our subscription should be created. All right, now we have a subscription. Basically, this is the account where we're going to fund it, and then we can use that account for all of our randomness requests. So I'm going to go ahead and just put in 10 Link here. You can put in however much you want. The price in Link of every random number you request is going to be based on the current gas rates on a given chain, as well as the gas lane that you've chosen. All right, our funds have been added. Let's go ahead and add a consumer contract. So it's asking us for a consumer address. We don't actually have a consumer address yet. So let's go ahead and jump over to the documentation and create a contract that is going to request a number. So if you scroll down, you're going to see this VRF v2 consumer.sol contract that we can open in Remix. Let's just jump right there. We're going to notice a few different things in this contract. At the top, we've got some imports. So now you've got VRF consumer base version 2. We've got an interface for the VRF coordinator, and then also a reference to the Link token interface. So all of those are specified for you on the Rinkeby network here in the example code. And then you can refer to the documentation for whatever chain you're going to be deploying to. And then you're going to see a few new options here. So the key hash option is the way that you specify that gas lane that was described in the documentation. So depending on the key hash you choose for the given chain you're on, the gas limit will be set differently for your random number request. So for example, on Ethereum mainnet, we have a 200 GUI key hash, a 500 GUI key hash, and a 1000 GUI key hash. You can also see in our contract here that we have a callback gas limit that you're in charge of. So depending on how much gas you're willing to spend in the fulfill random number, you should set this value appropriately. Next up is request confirmations. So it was something in VRF v1 that you could not control, but here now, depending on the chain you're on, depending on the request and the type, nature of the request you want to make, you can actually change this number. And then one of the most important and useful features that gives you a lot more flexibility and control of your VRF is you can actually specify the number of random numbers you want. And so you specify the num words, and then that will specify how many random UINT 256s you get back from the network. All right, here in the constructor, we're going to see a address for the coordinator and address for the link token. And then you'll see that the subscription ID is going to be created as we deploy the contract. And so I'm going to go ahead and get that. So if you remember when we created the subscription, after we funded it, we see the subscription ID. And now when I deploy this, I'm going to use that subscription ID. And we've got two methods that should look very familiar. We've got fulfill randomness method that takes in the randomness. This is going to be fulfilled by the VRF Oracle, as well as you've got request random words, which is how we're actually going to initiate that request to the Oracle. So I think we're actually already ready to go ahead and deploy this. So let's jump to the deploy screen here and select the right contract, which in our case is VRF v2 consumer. And I'm going to make sure that I am on injected Web3 so that we can actually deploy to the Rinkeby network. And I'm going to paste in the subscription ID here, and I'm going to deploy. Let's go ahead and pay for that transaction. And as soon as that is confirmed by the network, we'll show up here, and we'll be able to copy this address and then add that as a consumer and authorize this contract to use my subscription account. So let's go ahead and authorize this with another MetaMask transaction. All right, we can now view our subscription. We can see how much link we funded it with, and we can see our consumer contract. So now by doing this, we've authorized our consumer contract to make requests for randomness. So let's go ahead and make a request for randomness here. So we're going to go back to our contract that we deployed here, and we're just going to use the Remix interface here to keep things simple. And I'm going to request some randomness. So obviously this is going to use all of the configuration that I specified in my contract, just kind of hard-coded here. So we're going to get 2 words of randomness here. So we're going to hit request randomness, confirm the Rinkeby transaction. And then as soon as that transaction comes back, we should notice that we actually have a request. And then what we'll be doing is we'll be waiting for the Oracle to call fulfill random words on our contract. And then we'll be storing all of those random words in this sRandomWords storage variable. Let's go ahead and check to see if our random numbers come back from the Oracle. So I'll go in here into random words and let's request the 0th item of the array. Looks like we've got a random number there. And because we requested 2 random numbers, we should also have an item in index 1. All right, we've got our randomness there. And if we go back to the subscription manager app, you're going to see that there's actually an event history item here. We'll see that we spent about 0.33 link to get those 2 random numbers. We've just taken a journey to see what it looks like and feels like to use VRF version 2.
Now that we've learned a little bit more about Chainlink VRF, I hope that you took some time to go to docs.chain.link and play around with it a little bit so that you understand what's really going on. We're going to use this sample contract in here to create our function that's going to pick our random winner. This is an on-chain contract that coordinates with a verifiably random Chainlink node to give us a random number. You could look at the code directly on chain, or you can come right to the Chainlink GitHub and look at all the code for how this is actually happening provably and randomly. And we'll have a link to this in the GitHub repo associated with this course. So we're going to create our function here called pick random winner. This function is going to be called by the Chainlink Keepers network so that this can automatically run without us having to interact with it. And actually, while we're updating this, I want to add some stars here saying view/pure functions. Now our pick random winner function, we're actually not going to make public, we're going to make external. External functions are a little bit cheaper than public functions because Solidity knows that our own contract can't call this. We're actually going to change the name of this function as well very soon, but we'll get to that in a little bit. So in order for us to pick a random winner, we actually have to do 2 things. We first have to request the random number, and then once we get it, do something with it. So Chainlink VRF is a 2-transaction process, and this is actually intentional. Having random numbers in 2 transactions is actually also much better than having it in 1. If it's just 1 transaction, then people could just brute force try simulating calling this transaction, and we'll learn how to simulate calls soon. Simulate calling these transactions to see what they can manipulate to make sure that they are the winner. We want to make sure that this is absolutely fair and nobody can manipulate our smart contract into having them be the winner of the lottery. This function is actually going to request it, and then in a second function, the random number is going to be returned, and in the transaction that we actually get the random number from the Chainlink network, that's when we're going to actually send the money to the winner. And if we go to the Chainlink documentation, the function that the Chainlink node calls is this function called fulfill random words. This is going to be the requesting one, which we could even change this to request random winner to make it more clear. And then we'll make function fulfill random words. And this is going to be an internal override, which we'll explain in a little bit. Now, fulfill random words basically means we're fulfilling random numbers. The word comes from a computer science terminology, but you can basically just think of this as fulfill random numbers because we can get multiple random numbers. Now, in order to make our raffle contract VRFable, we have to import the Chainlink code. We can go back to the documentation and we're just going to grab this bottom line and we'll grab the top line in a second. So we're going to do import. I'm going to write it out, but if you want to copy paste it, you can at chainlink/contracts/src/v0.8/VRF consumer base v2.sol. And since we're importing at chainlink/contracts, we're going to need to add that in by running yarn add --dev at chainlink/contracts. Now that we have this in here, we should be able to import like so. And we're going to need to make our raffle VRF consumer baseable. We're going to need to inherit VRF consumer base. Go into our node modules at chainlink src v08 VRF consumer base v2. It comes with this function fulfill random words, and you can see it's an internal virtual function. Virtual means it's expecting to be overridden. The reason that it's in this VRF consumer base v2 is so that the VRF coordinator, which we'll use in a bit, knows that it can call this fulfill random words function. And this is the function that we're overriding. So back in our raffle.sol, we're going to inherit it by doing is VRF consumer base v2. And now, if we scroll down to fulfill random words, we can add in the input parameters, fulfill random words, which are going to be UN256, request ID, and UN256, a memory array random words. And if we hit save, our linter will now notice, okay, this is what I'm expecting. I'm expecting us to override fulfill random words, which takes these parameters. Now, if we look in our docs, in our constructor, we need to pass the VRF consumer base v2's constructor and pass that VRF coordinator. Again, this VRF coordinator is the address of the contract that does the random number verification. So right next to our constructor, we'll add the VRF consumer base v2 constructor, and we need to pass the VRF coordinator v2 address. So in our main constructor, we'll add that as a parameter as well. So we'll say address VRF coordinator v2, and then we'll pass this as a parameter for the VRF consumer base v2. Now that we have that, we shouldn't see that little underscore anymore, and we should be able to run yarn hardhat compile. Awesome, and we can see compiled 2 files successfully, and our code is working great. Now, something that I often do is I actually hate running yarn hardhat all the time because that's too many keys for my little brain to work with. I would prefer to write as little keys as possible. Hardhat also would like us to write as little keys as possible. So Hardhat comes with a shorthand and autocomplete. Hardhat shorthand is an npm package that installs a globally accessible binary called HH that runs the project's locally installed Hardhat and supports shell autocompletion for tasks. So what we can do is we can install it with npm like this, but we're going to install it with yarn. We're going to run yarn global add hardhat shorthand. And what this is going to do, we can see here, installed hardhat shorthand with binaries HH and hardhat completion. Now, instead of running yarn hardhat compile, which we can still run, we can just run HH compile. Running HH is going to be the same thing as if we had just run the hardhat command for our local directory. So now we need to actually have our request random winner function request a random winner. So let's go back to the documentation and we'll see how to do that. We can look at this function request random words and see exactly how it works. On the VRF coordinator address, we go ahead and call this request random words function. We're going to need to call this function on the coordinator contract. To get the coordinator contract, we're going to use the VRF v2 coordinator interface and the VRF coordinator address. So we're going to want to keep track of those. We can do that once again in our constructor. We have the address being passed to our VRF consumer base. Let's also keep it as a state variable for us. First, let's get the interface so we can interact with that contract. We can import that from Chainlink as well by doing import at chainlink/contracts/v0.8/interfaces/VRF coordinator v2 interface.sol. And now that we import this interface, same as we did with price feeds, we can do VRF coordinator v2 interface, VRF coordinator, and then we can save this VRF coordinator using the address. So we can say VRF coordinator equals this address VRF coordinator v2. And we're just going to wrap that address around the interface so that now we can work with this VRF coordinator contract. Now we're only going to set our VRF coordinator one time, right in our constructor. So what's the best thing that we can do here? Private immutable? You gosh darn right. Let's do private immutable VRF coordinator, and we'll change the name to I_VRF coordinator so that we know that VRF coordinator is indeed an immutable variable. In order to request the random word, we need to give it a number of parameters. I'm going to go ahead and copy this line into our contract just so that we can talk about exactly what's going on with it. And we don't need the S request ID. And instead of coordinator, we're going to do I_VRF coordinator. So we're going to call request random words on that VRF coordinator contract. And we need to pass it the key hash or the gas lane. I prefer calling it the gas lane. If we go to the Chainlink docs, we go to contract addresses, and we scroll down, we can see different gas lanes and different configuration parameters for different networks. This key hash is going to be the gas lane of the key hash, which tells the Chainlink node the maximum price you're willing to pay for your gas and way. If, for example, gas prices skyrocket and it's going to cost you a ton of money to get that random number, setting a ceiling will make it so that that random number doesn't come back. For us to pick a gas lane, we're probably going to want to have this gas lane or this key hash stored somewhere. So let's go ahead and make that a parameter of our constructor as well, and we'll save that as a state variable. So we'll do comma, bytes 32, gas lane or key hash or whatever you want to call it, and then we'll make a new state variable. And we're only going to set this once, so we'll make this a private, immutable, I_gas lane. And then we'll say I gas lane equals gas lane. So now we can just swap this out for I_gas lane. Okay, what's next? We need a subscription ID. The subscription ID is going to be the subscription that we need for funding our requests. There's actually a contract on chain which we can use to fund any subscription for any of these external data or external computation bits. And in this contract, there's a list of these subscriptions for people to make requests to. So we need the ID of the subscription that we're using to request our random numbers and pay the link Oracle gas. The subscription ID is probably also going to be something we're going to pass as a parameter to our lottery. So once again, let's scroll up to our constructor. We'll add a new parameter. And our subscription ID actually doesn't need to be a uint 256. It can actually be a little bit smaller with a uint 64. So we'll pass a uint 64 subscription ID. We'll make a uint 64. Since we're only going to set this once, we'll make this a private immutable I_subscription ID. Down here, we'll say I subscription ID equals subscription ID. All right, awesome. So now we can change this to our subscription ID. Okay, what's next? Request confirmations. Request confirmations is a uint 16, which says how many confirmations the Chainlink node should wait before responding. So if you make a request and there's only one block confirmation, maybe you don't actually send it because you're afraid of some type of blockchain reorganization or something. We're not going to worry too much about this, and we're actually just going to make this a constant of 3. So we're not even going to have this be parameterizable. We're going to have this one be a constant. So we'll say a uint 16 private constant request confirmations equals 3. And we're using the caps lock and underscores for our constant variables here. And now we'll grab request confirmations and stick it in right here. What's next? Callback gas limit. The callback gas limit is going to be the limit for how much gas to use for the callback request to your contracts to fulfill random words. This sets a limit for how much computation our fulfill random words can be. This is a good way to protect ourselves from spending way too much gas if, for example, we accidentally code our contract in a way where fulfill random words is incredibly gas expensive. It'll block the random number from responding. We are going to make this parameterizable because we want to change it depending on how we code our fulfill random words. So in our constructor, let's add one more. We'll add uint 32, since the size of this is a uint 32, callback gas limit, and we'll save this up top as a uint 32 private immutable I_callback gas limit, and we'll save this. I callback gas limit equals callback gas limit, and then we'll take this and we'll stick it here. All right, we got one more. Number of words. This is going to be how many random numbers that we want to get. We only want one. So we're going to go back up to the top We're going to create a uint32, and we'll make this also a private constant, numWords equals 1. Because we only want one random number. And then that'll be the last thing we need to add for our ivref coordinator.request random words. Now this request random words function returns a request ID, a uint256 request ID, a unique ID that defines who's requesting this and all this other information. If we want to save it, we can do uint256 request ID, ivref coordinator, request random words. Now, for now, we are going to emit an event with this request ID, and we'll go over why we're going to do that a little bit later. Create a new event at the top, and we're not going to follow the naming convention here because we're going to change the name of our functions a little bit, but we're going to call this requested raffle winner. And we're going to take a uint256 indexed request ID. Down here, we're going to do emit requested raffle winner request ID. And now we have a function that we can use to request a random winner using Chainlink VRF. Now, again, we're going to set this up so that the Chainlink keepers call this on an interval, but we'll do that in a little bit. For now, let's figure out what to do once we get that random number. Well, once we get that random number, we're going to want to pick a random winner from our array of players up here. So what do we do? Well, let's go in here. And let's pick a random winner using something called the module function. Now we're going to get an array back of random words or random numbers, if you will. Since we're only requesting one random word, this random words array is going to be of size 1 with one random word in it. Now this random word is a uint256. So this random word could be something like bliss. Well, obviously without the hyphens, but it could be something absolutely massive like that. Our players array is only going to be so big. So how do we get a random winner from this potentially massive random number? We can use something called the modulo function. The modulo operation a mod n yields the remainder r after the division of an operand a by the blah, 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 blah. So what does this mean? Well, we can use the mod function to get a random number out of our players array. So let's say our players array, or excuse me, our S players array is of size 10 and a random number is 200. So how do we pick a random person out of this players array? Or well, let's say our random number is 202. If we do 202, which is our random number, mod 10, we're going to basically do 202 divided by 10. But instead of having the decimals, we're just going to say, okay, how many times does 10 evenly divide into 202? And what's the remainder? What doesn't divide evenly into 202? Well, 20 times 10 equals 200 with 2 left over. So 2 doesn't evenly divide or multiply into 200. So that means 202 mod 10 is going to equal to 2. So that's how the module function works. And we can use that so we're always going to get a number between So we're always going to get a number here between 0 and 9, which works out perfectly because those are the indexes of the 10 people in our array. So let's use that here. We'll say a uint256 index of winner is going to be equal to random words at index 0, because we're only getting one random word, module the s underscore players dot length. So this will give us the index of our random winner. To get that address of the winner, we'll do address payable recent winner equals s players at this index of winner. So awesome. So now we'll have the address of the person that got this random number, the person's that's going to be our verifiably random winner. Now, it might be kind of cool to brag to people that you're the recent winner. So let's go ahead to the top and we'll create a new state variable for our most recent winner. Make this state variable in a new section called lottery variables. We'll say address private s underscore recent winner, and it'll start out as nobody, but as we get winners, update it with s recent winner equals recent winner. And we'll probably want people to know who this recent winner is. So down below, we can do function get recent winner. This is going to be a public view that's going to return that address. And then we'll just say return s underscore recent winner. Since again, the recent winner is going to be a storage variable. So now that we have a recent winner, what else are we going to do? Well, we're probably going to want to send them the money in this contract. So we're going to do exactly what we did before with sending the money. We're going to do that bool success, comma, blank equals recent winner dot call. We're going to say value is going to be address of this dot balance. We're going to send all the money in this contract and we're going to pass it no data. And now we could say require, success, whatever. We're going to be a little bit more gas efficient here. And we're just going to say if not success, then we're going to revert a new transfer failed error. So we're going to go to the top. We're going to say error. Name of the contract is raffle __ transfer failed, like that. Then go back down and we can now do revert raffle transfer failed, like that. And now that we've picked a winner, right now we don't have a way to actually keep track of the list of previous winners. So we're just going to omit an event. So there's always going to be that easily queryable history of event winners. So we're going to create a new event in the events section called event winner picked. And this is going to be an address indexed winner. And we'll scroll down and we'll do omit winner picked with the address of the recent winner. This looks pretty good. This looks pretty good here. Now you'll notice our request ID has this little underscore here. And it's saying, hey, it's an unused function parameter. Since we don't use this, but we still need fulfill random words to take a request ID and a random words array, but we don't use request ID, we can just comment out just the request ID part like this. This tells our function, hey, yes, we know that you need a uint 256, but we're not going to use the request ID. So we'll leave it in here, but we'll leave it blank. Now let's run a little compile here. We'll use yarn hardhat compile or compile. We'll see if we're coding things correctly. And indeed, we don't see any errors. So perfect. We can continue. So we've added the Chainlink VRF way. We have a way to verifiably get a random winner. This is fantastic. Now let's update this contract so that not only can it pick a verifiable winner, but it can also do this all programmatically and automatically trigger picking a random winner based off of some time interval without us having to interact with it and in a decentralized context. In order for us to automatically trigger smart contracts based off of some parameter, be it a time parameter, maybe the price of some asset is some number, maybe there's a certain amount of money in a liquidity pool, or really whatever trigger that you want, we can use Chainlink Keepers to do this. Stephen Fluin has done, once again, an amazing introduction to Chainlink Keepers, so we're going to follow along with another sub-video section of Stephen explaining Chainlink Keepers to us. He's going to be using the Kovan testnet, but be sure to use whatever testnet is in the documentation when you play with this and you try this.
My name is Stephen Fluin. Today I want to show you how to use the Chainlink Keeper network in order to automate your contracts and give them access to off-chain computation. Let's go ahead and dive in. So what we're going to look at today is we're going to start on the Chainlink documentation webpage. And if you just scroll down a little bit, you're going to find using Chainlink Keepers. Now, there's really two parts to building a Chainlink Keeper upkept smart contract. So the first thing is you need to write a smart contract that's compatible by implementing these two methods. And then second, you want to register that smart contract for upkeep with the Chainlink Keeper network. So let's go ahead and do both of those things. So let's start off just by copying and deploying this sample code that we've got with this one click to remix. What we're going to see here is a very, very simple contract that is just a simple counter. So we can see it's got a counter here. So it's got just a simple number. And then you're able to specify when you create the contract an update interval. And then the contract is going to verify, hey, has enough time passed? And if it has, let's update the counter. And you're going to notice that Chainlink compatible or Chainlink Keeper network compatible contracts use two really important methods that are part of this Keeper compatible interface. The first is check upkeep. And check upkeep is special because this is where the off-chain computation happens. So this is a method that's not actually run on-chain. This is run off-chain by a node from the Chainlink Keeper network. And so what's really nice about this is that the gas used here isn't actually gas that's on-chain. So this is just being run by a Chainlink node. And then what happens is if your check upkeep method returns that upkeep is needed, then it's going to go ahead and perform upkeep on chain. So you can actually generate data off chain and then pass that in. That's called the check data. And then that becomes the perform data that's passed into perform upkeep. And so the perform upkeep method is where you're going to want to verify that things are correct and that things actually should be modified and run on chain, and then actually make the state change. And so let's go ahead and compile this contract and deploy it to the Kovan network. So let's go ahead and within Remix, we can do this compilation and we're going to compile and deploy directly to Kovan. So the Chainlink Keeper network is currently, as of the filming of this, available on both Kovan as well as the Ethereum mainnet. And let's go ahead and deploy the counter contract. And let's say let's not update more than every 30 seconds. And so let's go ahead and deploy. So MetaMask is going to ask for a little bit of payment in order for me to deploy this contract to the Kovan network. And it looks like that is live. So now what I'm going to be able to do is I'm going to be able to take this Keeper contract and copy its address. And now we're going to register that contract for upkeep. So we're going to jump over to the application that powers the Chainlink Keeper network. There's a few different ways you can do this. You can interact directly with the registry contract, but there's a very, very nice interface that lets you do this. So let's go ahead and register a new upkeep, and it's giving me an error that says you need to connect your wallet. So let's go ahead and do that. So I'm going to just connect wallet here, and I'm going to give it access to my account. And then from there, we should actually be able to register. So I'm going to use an email address here. I'll give my contract a simple name. I'll paste in that address from the deployed contract, and then I'll give it a gas limit. And then check data is this special thing where you can actually register multiple upkeeps on the same contract and pass in data to specify how you want check upkeep to be run. But we're just going to ignore that. That is an optional one. And then we'll give it a starting balance of around 10 link. It's going to go ahead and use MetaMask again to register that transaction on the network. And once it's confirmed, my upkeep should be registered with the network and funded with 10 link to kick things off. All right, if we go ahead and view the upkeep, we can see it's registered. And as soon as the next round of the Keeper nodes executes, which should be roughly about every block, we should see that the check upkeep method is going to return that, hey, upkeep is actually needed because the timestamp is more than 30 seconds ago. And then we should go ahead and perform upkeep. So as soon as I take a look at this in Remix, I can actually make this bigger here. We're going to be able to see from the methods of the contract, if we check the counter, it's going to start at 0. And as soon as that 30 seconds has passed, we'll be able to hit the counter again. And we'll see that the Chainlink Keeper network has performed upkeep on my contract. All right, we just refreshed and we see that the balance of the upkeep has been decreased by about 0.01 link. And we should also see within our contract that our counter has now updated via that perform upkeep method call. And now our counter is at 1, showing us that our contract is being upkeeped by the Chainlink Keeper network, and everything is working exactly as we expect. So as you can see, it is very, very easy to create a contract that is compatible with the Keeper network, and it's very, very easy to register that upkeep and start seeing that your contract automation and off-chain computation are working flawlessly.
Now that we've learned a little bit more about how Chainlink Keepers work, if you want to take some time to go through the documentation and open up way down below this open and remix button so you can actually work with one of these and see these in action for yourself on a testnet, feel free to do so. We're going to be using a setup very similar to this Keeper's counter setup in the Chainlink documentation. So now let's update our code so that this request random numbers automatically happens using Chainlink Keepers. And if we look at the example contract, you can actually read more about what's really important for this to work. And we need a check upkeep and a perform upkeep function in our code. So instead of request random winner, this is going to be the perform upkeep that we're going to change. But first, let's make this check upkeep. The check upkeep function is basically going to be checking to see, is it time for us to get a random number to update the recent winner and to send them all the funds? So let's go ahead and make that function. I'm going to add some notes here just so that it's clear what's going on. And maybe I'll even do natspec to tell developers what's going on with this function. So we're going to create this function, check upkeep. And if we look at what this needs, it needs to be external override. External override. And if we see this override keyword, this means that, okay, there's probably a perform upkeep somewhere else. And if we scroll to the top, and we're going to import this keeper compatible interface so that we make sure that we implement both check upkeep and perform upkeep in our code here. If you want, you can just import keeper compatible in here or just the keeper compatible interface. In our code, we're going to do import at chainlink /contracts/src /v0.8 point interfaces /keeper compatible interface.sol. And now we're just going to say contract raffle is VRF consumer base v2 and keeper compatible interface. And this keeper compatible interface inheritance just makes sure that we add check upkeep and perform upkeep, which we're going to add in a little bit. And if we look back at the docs, we can see check upkeep takes a bytes call data check data as an input parameter. So we'll do bytes, call data, check data as a parameter. Now this check upkeep bytes call data allows us to specify really anything that we want when we call this check upkeep function. Having this check data be of type bytes means that we can even specify this to call other functions. There's a lot of advanced things you can do by just having an input parameter as type of bytes. For us though, we're going to keep it a little bit simple, and we're actually not going to use this check data piece. So similar to how below, we're not using request ID, we can just comment it out. However, we still need to make sure that this parameter is type of bytes call data. Now, anyways, let's go ahead and annotate this check upkeep function. We'll say this is the function that the chainlink keeper nodes call. They look for the to return true. Look back at the documentation, we can see that this check upkeep returns both an upkeep needed and a perform data, which again, we're going to ignore. This upkeep needed is going to be true or false. If it's true, that means it's time to get a new random number. The following should be true in order to return true. So in order for it to be time to request a random winner, what should happen? Our time interval should have passed, which we haven't defined yet, but we will. The lottery should have at least one player and have some ETH. And then our subscription is funded with Link. Similar to how with Chainlink VRF, your subscription needs to be funded with Link, the same thing needs to happen for check upkeep and keepers to run. Your subscription needs to be funded with Link. Now we're going to add one more additional piece here. We're going to say for the lottery should be in an open state. Something that we want to avoid when we're waiting for a random number to return and when we've requested a random winner, we're technically in this weird limbo state where we're waiting for a random number to be returned and we really shouldn't allow any new players to join. So what we actually want to do is create some state variable telling us whether the lottery is open or not. And while we're waiting for our random number to get back, we'll be in a closed or a calculating state. Now, what we could do at the top of our contract, we could just say Boolean private s underscore is open. And we could just set this to true if we're open, otherwise false. Well, what if we have a ton of different states? What if we want it to be like pending, open, closed, calculating, etc.? What do we have a ton of different states? Well, we could make this a UN256 private s underscore state. And we could just keep track of the state, having like 0 be pending, a 1 be open, 2 be closed, 3 be calculating, etc. But this can be a little tricky to keep track of. So a better way to actually keep track of all this in our code is to use an enum. Enums can be used to create custom types with a finite set of constant values. So we could create, for example, a state created, locked, inactive, and it's basically a new type for our smart contract. For us, we're going to create a new type. And if we go back to the layout of variables in our smart contract, types should actually be first thing in our contract. So we're going to create an enum called raffle state. And for now, and we're just going to have it be open. We're just going to have it be open or calculating. Now, when we create an enum like this, we're kind of secretly creating a UN256 where 0 equals open and 1 equals calculating. However, this is much more explicit that we know what each one of these numbers actually means. Now that we've created this new type called raffle state, we can create a new lottery state variable of type raffle state. So the exact same way we declare any other variable, we'll name its type, which is going to be raffle state. And this is going to be a storage variable. So we'll go ahead and do private s underscore raffle state. In our constructor, right when we launch this contract, we should open up this raffle. So we'll say s raffle state equals, and we could use a UN256 wrapped in type raffle state like so, or we can be more explicit and say raffle state dot open. Now we know that the raffle state is in an open state. When we only want check upkeep to work is if the lottery is actually open. Additionally, we probably only want people to be able to enter if the lottery is open. So let's go ahead and create another if statement and revert if the lottery isn't open. So we can say if s underscore raffle state does not equal raffle state dot open, then we're going to revert with a new error we're going to create, raffle underscore underscore not open. And then of course, at the top, we'll create error, raffle not open. Now, additionally, let's go down. When we're requesting a random word, let's update the state to be calculating so other people can't jump in here. So right above our VRF coordinator.request random words, we'll do s_raffle state equals raffle state dot calculating, so that nobody can enter our lottery and nobody can trigger a new update. And then once we fulfill, after we pick our winner, we'll say s raffle state equals raffle state dot open again. And something else that we forgot to do was after we pick a winner from S players, we need to reset our players array. So let's add that in here as well. S players equals new address payable array of size 0. So we'll reset the raffle state and we'll reset our players array. All right, great. So now that we've learned about enum, let's add it to our check upkeep here. We're going to check these 4 things, and if they all pass, check upkeep will be true and will trigger the chain link keepers to request a new random winner. So first we'll say bool is open is going to be equal to raffle state dot open equals s_ raffle state. So you can think of that as this boolean is open is going to be true if raffle state is in an open state, and it'll be false if raffle state is in any other state. So great, we have an is open boolean that we can check later on. What else do we need? Well, we need to check to make sure our time interval is passed. Well, we don't have a time interval yet, so let's create a time interval. In order to check the time, we can use another one of Solidity's globally available variables with block.timestamp. Block.timestamp returns the current timestamp of the blockchain. To get the current timestamp, we're going to need block.timestamp. But to get if enough time has passed, we're going to need to get the current block.timestamp minus the last block timestamp, which we don't have yet. Let's go ahead and create a state variable to keep track of the previous block timestamp. So this is going to be a new state variable that we're going to make. We're going to say uint256 private s_ last timestamp. And right when we deploy this contract, we'll update this with the current timestamp. S last timestamp equals block.timestamp. All right, awesome. Now we have a last block timestamp, but we're going to need to check that the difference between the current timestamp and the last timestamp is greater than some interval. So we also need to create an interval. And this is going to be some interval. This is going to be some number in seconds of how long we want to wait between lottery runs. So let's go ahead and add this to our constructor as well. We're going to do a comma here, and we'll do uint256 interval, and we're going to create another global variable, uint256 private s_ interval. And in our constructor, we'll say s interval equals interval. Now, interval isn't going to change after we set it. So instead of making a storage variable, let's make it an immutable variable to save some gas. Okay, perfect. Now that we have all this, we can actually create a boolean to check to see if enough time has passed. So we'll say boolean time passed equals the current block.timestamp minus s_ last timestamp. And we should check to see that this is actually greater than I_ interval. So we have a boolean to check to see if we're open. It'll be true if we're open, and we'll have a boolean to see if enough time has passed. This will be true if enough time has passed. What else should we check? Well, we should check to see if we have enough players. So we'll do a boolean has players equals, and we'll check to see if s_ players dot length is greater than 0. If s players dot length is greater than 0, has players will be true, otherwise it'll be false. And we'll also see if we have a balance. So we'll do boolean has balance equals address this dot balance is greater than 0. Then finally, we're going to take all of these booleans and turn them into the return variable that we're looking for. We're going to say boolean upkeep needed equals is open and time passed and has players and has balance, like that. So all of these combined is going to be this boolean upkeep needed. And if this returns true, it's time to request a new random number and it's time to end the lottery. If this is false, it's not time yet. It's not time to end the lottery yet. Now, again, if we go to the Chainlink documentation, upkeep needed actually needs to return that Boolean upkeep needed and some bytes memory perform data. So we need to update our function here and say returns bool upkeep needed, comma, bytes memory perform data star slash. And since we've initialized Boolean upkeep needed up here, we don't need to say what type of upkeep needed is down here, since this will automatically get returned. Perform data is something that we can use if we want to have check upkeep do some other stuff depending on how this check upkeep went. We don't really need it to do anything else, so we can just leave it as such. Great. So now we have a check upkeep. We have a way to check to see if it's time to trigger picking our random winner of our lottery or our raffle. Now that we learned how to actually do this trigger, let's write the function that gets executed after this returns true. This is going to be our perform upkeep function, which we can see an example again in the Chainlink documentation. Now, when it's time to pick a random winner, actually what we're going to do is we're just going to call this request random winner function. So instead of having this extra function, let's just transform our request random winner function into this perform upkeep. Since once check upkeep returns true, the Chainlink nodes will automatically call this perform upkeep function. So in function request random winner, let's rename this to perform upkeep, and we'll have it take the input parameter bytes call data perform data. Bytes call data perform data. If in our check upkeep we had a perform data, we would automatically pass it to our perform upkeep. We're not going to pass anything to perform upkeep, so we can leave it commented out like this. Since perform upkeep is actually identified in the keeper compatible interface, this is now going to have to override that function. Now we want to do a little bit of validation before we continue here, because right now anybody can call our perform upkeep function. So we want to make sure that it only gets called when check upkeep is true. An easy way for us to do that is to actually call our own check upkeep function. Now right now check upkeep is an external, so we actually can't call our own check upkeep function. So let's change it to public so that even our own smart contract can call this check upkeep function. Now that we've made it public, in perform upkeep, we can call check upkeep, pass it nothing, and then return the upkeep needed and perform data, which we don't really care about. So we'll get that bool upkeep needed, and then we don't care about perform data, so we'll leave that blank, equals check upkeep, and we'll pass it a blank call data. Now we want to make sure that this is true in order to keep going with the function. So we could write a require here, but we're going to do if not upkeep needed. Then we're going to revert with a new error that we create, raffle, upkeep not needed. And we're going to pass some variables to this error so that whoever is running into this bug can hopefully see why they're getting this error. So we'll pass the balance of this contract, just in case there's no ether in here. We'll add the players.length, just in case there's no players. And we'll add a uint256 s_raffle state to make sure that the raffle is actually open. And then of course, we'll need to create this error at the top. Error, raffle upkeep not needed, which is going to take a uint256 current balance, uint256 num players, and uint256 raffle state. Our code is starting to look really professional. This is awesome. Now, something that we forgot to do back in the fulfill random words is we actually forgot to reset timestamp. Every time a winner is picked, we want to reset the timestamp as well so that we can wait another interval and let people participate in the lottery for that interval. So we'll scroll down into fulfill random words, and right after we reset players, we'll also reset the timestamp. Okay, great. And I think we're just about done here. Let's add a little bit of NatSpec to make this look even more professional and give people who are reading our contract even more information. So let's add title here at title, and we'll say a sample raffle contract. We'll say at author is going to be me, Patrick Collins, or you can put your own name there as well. At notice, this contract is for creating an untamperable, decentralized smart contract. And then we'll do at dev. This implements Chainlink VRF v2 and Chainlink keepers. All right, awesome. We've got our type declarations. We've got our state variables. We've got lottery variables, which are still state variables. We've got our events. Now it's time for our functions afterwards. We've done a little bit of NatSpec, at least on our check upkeep. If you want to add some more NatSpec on things like enter raffle, perform upkeep, etc., you can absolutely do so. And then down at the bottom, we have our view/pure getter functions. Let's see, do we want any other getter functions here? Well, we probably want to give people the chance to get a raffle state. So we'll do function get raffle state. This will be a public view returns the raffle state. We'll say return s underscore raffle state. We probably want to give people the chance to get the number of words. And this is going to be a little bit interesting here. Ready? So if we do function get num words, public view returns uint256, return num words, you'll see something interesting happen here. If we pull up our compiler and run compile, hopefully everything works here. Oh, and everything doesn't work because I didn't import this correctly. Let's fix that. Let's try again. Oh, there's a couple things I missed. Let's fix splayers. This is why it's good to compile as you code. splayers.length. Let's try again. And I spelt interval wrong. I underscore interval. Let's try to compile again. See how many more spelling mistakes I made. And there it is. I underscore in. There we go. Let's paste that. And we do get another error here. Invalid type for argument in a function call. Invalid implicit conversion from literal string to bytes call data requested. Since we're passing this empty string here and check upkeep needs a call data actually doesn't work with strings. So we need to make this bytes memory instead. And our compiler is now happy with us. And I spelled timestamp wrong. That's a lowercase s. So, and you might see some squiggles here on check upkeep. We could make this a view function since we're not actually modifying any state, but I want to keep it public for reasons I'll show you a little bit later. But finally, we get the yellow squiggly that I was looking for here. And if we run compile, we should see a warning in our compiler as well. Okay, so we see all those yellow squigglies here. Unnamed return variable can remain unassigned. We need this bytes memory in here because that's what the keepers are looking for. Warning, function state mutability can be restricted to view for our function check upkeep. You can make it view if you want, but I'm going to keep it public for reasons I'll show you a little bit later. And finally, function state mutability can be restricted to pure. This is what I wanted to show you. Since num words is actually in the bytecode, since it's a constant variable, technically isn't reading from storage, and therefore this can be a pure function. Returning num words doesn't actually read in storage. It literally will go and read the number 1. So doing get num words in Solidity with num words being a constant variable is going to literally be the exact same as saying get 1, and we would return 1 here. We might also want to get the number of players. So we'll create a function get number of players, and this will be a public view. Returns a uint256. Return s underscore players dot length. We're also probably going to want the latest timestamp. So we'll do function get latest timestamp. Public view returns uint256, and we're just going to return s underscore last timestamp. And maybe we'll want to do request confirmations. So we'll do function get request confirmations. Public pure, since request confirmations is also a constant function, returns uint256, return request confirmations. All right, we've got some wonderful getters here, some view/pure functions. We have a way to get a random number. We have a way in a decentralized context automatically execute picking a random winner. We have a way for people to enter our raffle, to enter this lottery, and we have a bulletproof way to solve creating a truly fair, decentralized lottery. Oh my goodness. Let's do one more compile for good measure, compile. And these are just warnings, so we're good to go here. Our code is compiling successfully. Like I said, normally this definitely isn't going to be the way that you're going to write your smart contracts. It's almost impossible to write a full smart contract without making any mistakes and without flipping back and forth between the documentation. I have already written this contract many times myself, and I still made a whole bunch of mistakes. So it is totally reasonable and totally rational for anybody and everybody to make mistakes going through this, and to use resources and to write tests along the way. Now that we have our raffle.sol created, it's time to add everything else. So we're going to come over here, we're going to create a new folder and add our deploy folder per usual. And we're going to do exactly what we've already done a couple of times. We're going to create some scripts to deploy our raffle contract. Now with our raffle contract, there's a couple of things in here that we want to make note of. First thing is that our constructor right now is absolutely massive. There are a ton of parameters in here that we need to account for. Let's take a look at our constructors and see if there's any contracts that we're already interacting with. Okay, VRF coordinator v2, this is a contract address. Entrance fee, no. Gas lane, no. Subscription ID, no. Callback gas limit, no. And interval, no. So knowing that this is an address should be a tip that, okay, we're probably going to need to deploy some mocks for this, since we're going to need to interact with a VRF coordinator contract that's outside of our project. But let's go ahead and start working on our raffle deployment script first. And we know we're going to have to deploy some mocks, so we'll just keep that in mind. So let's create a new file, o1 deploy raffle.js. And let's get started deploying our raffle contract. Now, this is going to look really similar to what we've done before, and we're going to do it again here. If you want to use your previous deploy scripts as a reference, I absolutely recommend you do so. But let's get started with module.exports equals an async function. It's going to take get named accounts and deployments as input parameters. Then we're going to do const deploy log equals deployments. Then we're going to say const deployer equals await get named accounts. Let's go to our config and update module.exports to have this. I'm just going to copy paste so that deployer is going to be defaulted to account 0 and player is going to be defaulted to account 1. If you want to go ahead and write this out, feel free to pause and write out your named accounts right now. There's going to be a lot of boilerplate in our hardhat.config.js. So feel free to have the GitHub repo for this lesson up with you, or your previous scripts that you've already written as a reference. Named accounts, deployer, and we're also going to have a player named account so that we can separate different users or different players who are interacting with our contracts. But for now, we're going to grab our deployer and we're going to get started. Now, similar to last time, we would just do const raffle equals await deploy raffle, comma, and then add all of our stuff in here, right? So this would be from deployer, args. We're going to have a ton of args, so we're going to come back to this. And then log is going to be true. And then we're going to have wait confirmations. There's a little bit more boilerplate we need to work with here. In our Hardhat config, we don't have a network here. So let's add our network information so we can get those block confirmations. We'll be specific in here as well, and we'll say default network is going to be Hardhat. And then we'll say networks, and we'll add our network information. Definitely going to be working with Hardhat, which has a chain ID of 31337. Might as well put that in here as well. And block confirmations, we're just set to 1. We'll add this comma here. We're also going to be running some staging tests on the RinkB network. So we'll add RinkB in here with a chain ID of 4, block confirmations of 6, and we need to add a URL and then also some accounts. For our URL, we've done this 100 times. We'll do const rinkb rpc URL equals process.env dot rinkb URL. That's private key, blah, blah, blah. We're going to add all these same variables from our last projects. So I'm going to ask you to pause here and just copy paste all those variables from our last project. Boom, like so. Since we're adding a rinkb URL, private key, CoinMarketCap, and Etherscan, we're also going to want to make sure new file .env, and we're going to drop all of our information in here. A rinkb URL, private key, Etherscan API key, and then our CoinMarketCap API key as well. Now that we have our private key, our rinkb URL down in URL, rinkb URL, and for accounts, we're just going to add that single private key. So now for wait confirmations, it's going to equal network.config.block confirmations or 1. And we're going to have to import network from Hardhat, which it looks like my VS Code automatically did for me. Thanks, VS Code. So this is how we're going to deploy our raffle. Obviously, we have a ton of arguments that we need to account for, so let's get to it. Let's look at our raffle constructor to see what we need to get. Okay, well, the first thing that we need to get, VRF coordinator v2. We're going to use the same strategy we used in our FundMe project with using mocks if we're on a development chain and using the actual contract address if we're on a testnet or a live network. So let's get to it. So let's go ahead, recreate that helper hardhat config.js and create that const network config. Say it equals. For Hardhat, we're going to use a mock, so we don't need to put that in here for now. But for Rinkeby, let's go ahead, put a 4 in here. So the name is going to be Rinkeby. And we're going to need to go to the Chainlink documentation, the VRF contracts, and we're going to need to grab VRF coordinator for the Rinkeby testnet. So we're going to grab this address here, plop it in here. We'll say VRF coordinator v2. Bam, right like that. So back in our deploy raffle, we're going to have to pick whether or not to use the VRF coordinator v2 in the network config or some mock that we deployed, which of course leads us to us having to deploy a mock. So let's create that new file, 00 deploy mocks.js. So same thing, module.exports equals async function where it's taking get named accounts and deployments as its input variables from the Hardhat runtime environment. We do const deploy, comma log equals deployments, and then const deployer equals await get named accounts, like so. And then we're going to grab the chain ID as well, because we're going to only want to deploy this on a development chain. So we'll do const chain ID equals network.config.chain ID. Now we're going to only want to deploy mocks if we're on a development chain. So once again, we're going to go to our helper config. We're going to add those development chains in here. We'll say const development chains equals hardhat and localhost. And then we're going to want to export both of these. So module.exports equals network config and development chains. Now in our deploy mocks, we're going to want to grab those by saying const development chains equals require // helper hardhat config. Now we can check to see if development chains includes the network.name that we're currently on. If we're in a development chain, we're going to go ahead and log local network detected deploying mocks. And now we'll have to deploy a mock VRF coordinator. Where do we get a mock VRF2 coordinator? Well, let's go ahead and create one of those. We go to the Chainlink GitHub again. We go to contracts, SRC 0.8. They actually have a mocks folder with VRF coordinator v2 mock.sol. And we're just going to use this as our mock. So in our contracts folder, we're going to create a new file called test, a new file called VRF coordinator v2 mock.sol. And we're just going to import this mock and have it be our mock. So we'll do spdx. We'll do pragma solidity caret 0.8.0 or 7 or whatever we want to do. We'll do import at chainlink /contracts /src /v0.8 /mocks /vrf coordinator v2 mock.sol. And we'll just check to see if it compiles with hardhat compile. And it looks like it's compiling as well. Awesome. So now that we have our mock contract, we can actually go ahead and deploy it. So we'll do await deploy VRF coordinator v2 mock, comma, and then we'll give it our parameters in here. We'll say from deployer log is going to be true. And then we're going to do our arguments. Now, what are the arguments of this VRF coordinator v2 mock? Well, if we open the VRF coordinator v2 mock right in our VS Code or on GitHub, we can actually see, if we roll over to the constructor, that it takes two things. It takes a base fee and a gas price link. What are these? The first one is this const base fee. If we go back to the documentation, we can see that there's this premium section of 0.25 link for Rinkeby. This means that for each request, there's a base fee of 0.25 link for every request. So anytime we want to request a random number on Rinkeby, it's going to cost us 0.25 link, or you can think of it as 0.25 Oracle gas to make this request. So back in our deploy mocks, we can say base fee equals, we could resemble Rinkeby here and do 25 blah, 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 or we could do ethers.utils.parseETH of 0.25. I'll even put a little comment here. Say 0.25 is the premium. It costs 0.25 link per request. And remember, the reason that this costs 0.25 link per request versus the price feeds didn't cost anything is because the price feeds, if we look back at data.chain.link, each one of these price feeds is being sponsored by a group of protocols who are paying for all these requests already. Since there isn't a sponsor for this, we are the only ones requesting the randomness. We get to be the ones to actually sponsor getting this random number. Then the second thing here is going to be this gas price link. So let's create another const here. We'll do const gas price link. But what this is actually a calculated value. This is a calculated value based on the gas price of the chain. Here's an example. If we were to request a random number on Ethereum and the ETH price skyrocketed up to like $1 billion, gas would be incredibly expensive. Now, when Chainlink nodes respond, Chainlink nodes pay the gas fees to give us randomness and do external execution. The Chainlink nodes are actually the ones that pay the gas when returning randomness or executing an upkeep or etc. If we go to our raffle.sol and scroll down to perform upkeep or fulfill random words, it's actually the Chainlink nodes that are calling these two functions and paying the gas for it. They get paid in Oracle gas to offset those costs. But if the price of ETH or any native blockchain skyrocketed, the Chainlink nodes would still have to pay the gas fee. So the Chainlink nodes have a calculated variable called the gas price per link, which fluctuates based off the price of the actual chain so that they never go bankrupt. So basically, the price of a request changes based off the price of gas for that blockchain. You can kind of think of this as the link per gas, if you will. For now, we can kind of just set it to whatever we want, and we'll just set it to 1E9, which is going to be equivalent to 1, 2, 3, 4, 5, 6, 7, 8, 9. So now that we have the base fee and the gas price link, we'll grab this base fee. We'll have these be the arguments for our VRF coordinator v2 mock. So we'll say, and actually we can delete that. We'll say const args equals base fee and gas price link. Then we can take this args variable and just plop it in here. Now we can do log mocks deployed. And then we can do log, do a little line like this to let people know that this deploy script is done. Then we'll just do a module.exports.tags equals all and mocks. So now that we have a VRF coordinator v2 mock deployed, we can come back over to our raffle and make some code around it. Similar to what we just did with our deploy mocks, we can say if development chains dot includes network.name, we'll do some stuff. And we need to import development chains from our helper Hardhat config, and we need to import network from Hardhat. My VS Code automatically added them. Wow, thanks VS Code. Let's even just do const args and make this variable down here. Stick it in args. Our first argument is going to need to be this VRF v2 coordinator. So let's make a variable. We'll say let VRF coordinator v2 address. And if we're on a development chain, we're going to grab that mock contract. So we'll say const VRF coordinator v2 mock equals await ethers.get contract VRF coordinator v2 mock. And then we can set VRF coordinator v2 address equals VRF coordinator v2 mock dot address. Cool. We have the address here. Else, if we're not on a local network, the VRF v2 coordinator address is simply going to be derived from our network config. So let's import the network config as well from our helper Hardhat config. And we'll say else VRF coordinator v2 address equals network config of our chain ID, which actually, sorry, we do need the chain ID, const chain ID equals network.config.chain ID. chain ID of VRF coordinator v2. Chain ID VRF coordinator v2. All right, perfect. We've got this set up to work with our VRF coordinator v2 address. What else do we need from our raffle? Well, we need an entrance fee. We probably want to change the entrance fee depending on what chain we're on. If we're on a more expensive chain, we might want to make this higher than others. So let's go ahead back to our helper Hardhat config and make an entrance fee based off of the blockchain. So for RinkB, maybe we want to make it 0.01 ETH. So we could say ethers.utils.parse ether of 0.01. And once again, thank you VS Code for automatically dropping that in for me. And we're also going to want an entrance fee for our Hardhat. We could also set a default in here, but let's just be a little bit more explicit. So we'll say 31337. The name of this is Hardhat. We don't need to give it a VRF coordinator v2 address because we're going to deploy a mock, but we do want an entrance fee, and let's just give it the exact same entrance fee here. So we'll say ethers.utils.parse ether 0.01 ETH. All right, great. So on our deploy here, we can just say const entrance fee equals network config chain ID of entrance fee. Let's start populating our args here. So the first one is going to be our v2 coordinator address. Next one is going to be our entrance fee. Got it. Got it. Now we need our gas lane. On RinkB and other networks, there are different gas lanes that we can choose from. Let's grab the only gas lane from RinkB, the 30 GUI key hash. Let's drop this, of course, into our network config as gas lane, pop it in here. For Hardhat, our mock actually doesn't care what gas lane we're working on because we're going to be mocking the gas lane anyways. So we can just say gas lane. We can just go ahead and use the same one, or really anything here. It doesn't really matter. Now here we'll say const gas lane equals network config chain ID gas lane. And we'll grab the gas lane and we'll stick it into our argument array. We've got this one. We've got this one. We've got this one. Now it's time for the subscription ID. Now, if you haven't run through docs.chain.link for the Chainlink VRF, I highly recommend you do so that you can understand what this subscription ID is. We know that we can actually make a subscription ID using that front end, using that website, vrf.chain.link, which is great and all, but what if we're on a local chain? So we can get a subscription ID, no problem in here, but it's a little bit harder on a local network. Now I'm actually going to teach you how to create and fund subscription IDs completely programmatically. So you don't even need to use the UI if you don't want to. However, for the purpose of this course, we're still going to use the user interface. We're still going to use that website for us to get our own subscription IDs, but you could 100% automate the process of creating a subscription ID and funding a subscription ID. Because when you create and fund subscription IDs, you're just calling create subscription and fund subscription on that smart contract. So on our development chain, we have our VRF coordinator v2 mock. And what we're going to do, and on our development chain, we're going to create that subscription. So we're going to say const transaction response equals await VRF coordinator v2 mock dot create subscription. And then we'll run const transaction receipt equals await transaction response dot wait, we'll wait one, block confirmation, and inside this transaction receipt, there's actually an event that's emitted with our subscription that we can get. This is another place where emitting events is incredibly helpful. So in fact, if we open back up that VRF v2 coordinator mock, and we look for create subscription, we see we emit subscription created with the subscription ID. We can actually get this event emitted from our transaction receipt. Now to assign it, let's go ahead and create subscription ID up here. And then we'll say subscription ID equals transaction receipt dot events of 0.args.sub ID. And again, be sure to watch that events video if you want to learn more about how to work with events in Hardhat. Now that we have a subscription, we need to fund the subscription. On a real network, you need the link token to actually fund the subscription. The current iteration of the mock allows you to fund the subscription without the link token. So what we can do is we can just run await VRF coordinator mock, VRF coordinator v2 mock dot fund subscription, and we'll give it the subscription ID, and we'll need to do some fund amount. For this, we can just create some variable. We'll say const VRF subscription fund amount equals ethers const.utils.parse ether of, we'll say 30 VRF subscription fund amount. We'll just paste that down here. We could do this as well for a real testnet or our live networks, but just so that we become familiar with the user interface, we're not going to do a testnet programmatically. And for a testnet, we're just going to use exactly what we've been doing so far, where we can put a subscription ID in our helper config. So we'll say subscription ID. We'll put something in here. Right now, we'll just leave it at 0, but later on, when we actually create a subscription, we'll update our subscription ID. And so we'll say subscription ID equals network config chain ID of subscription ID. Perfect. Now we can add this to our arguments array. What else do we need? Subscription ID, we need a callback gas limit. Our callback gas limit is going to vary network to network. So once again, we're going to go into our helper config here, callback gas limit. And for us, we'll set a pretty high limit of 500,000 gas. So we'll say callback gas limit of 500,000 gas. And for Hardhat, we'll do the same thing. So we can say const callback gas limit equals network config chain ID callback gas limit. We'll grab this, put it into our argument array. What else do we need? All we need now is the interval. So we can change this network to network as well. For Rinkeby, we'll say interval. We'll have it just be 30 seconds for both Hardhat and for Rinkeby. So we'll do the same thing here. We'll say const interval equals network config chain ID interval. And we'll grab this, pop it in the end of our array. Whew. All right, awesome. Now we have an argument array. You can drop it right in here and perfect. Everything in our constructor for our raffle contract. Great. This is looking fantastic. We've got wait confirmations, we got logging, arguments, deployer. Okay, well, what next? Well, let's go ahead and add that verification piece. So once again, create a new folder, utils, new file, verify.js. We can either copy paste this from our last project, or we can grab this from the GitHub repo associated with this course. Once we have our verify script in here, we're going to import it by saying const verify equals require ... helper hardhat config. And then we can add that same bit of code down here to verify our contract. We'll say if we're not on a development chain, and we have process.env.etherscan API key, then we're going to log verifying ... and then await verify raffle.address and the args. Now we'll just do a log of a whole bunch of hyphens to say that this script is done. Module.exports.tags equals, let's say this will be all and raffle. All right, so let's test this out. We'll do hardhat deploy or yarn hardhat deploy and see if this script works correctly. Looks like we ran into an error. Network config not defined. So let's spell this right. Network config. There we go. That looks much better. Let's try this again. It looks like our deploy scripts are working well. Local network detected, deploying mocks, deployed VRF coordinator v2 mock, mocks deployed, and then we went ahead and deployed our raffle. Awesome. This is massive. Now we're not going to test deploying this to a testnet quite yet because, well, we don't have any unit tests yet. We need to write unit tests before we want to ever test running this on a testnet. So we have our deploy script, we have our contracts. That means it's time for us to write some tests. We'll come over here, we'll create a new folder called test. And for now, we'll just make our unit tests. So unit tests. And in here, we can create a new file called raffle.test.js. And let's write some unit tests. Now for these unit tests, we are going to be a little bit verbose here. We're going to make our coverage really, really good here. It's not going to be perfect, but this is going to be pretty verbose. So I'm going to go pretty quickly here. So you can feel free to pause, slow me down, speed me up, whatever you need to learn this section. It is really good muscle memory to go through writing these tests and understand what you should be thinking about when you're writing these tests. So feel free to speed up the parts that you already know and slow down the new parts because we are going to go over some new information here. Writing tests may seem like a tedious process, but I promise as you get better at writing these tests, you'll realize that these are the things that you can rely on when stuff doesn't work and when you're not sure how to code something. Getting this muscle memory down, writing these tests is going to make you a fantastic engineer. So let's go through and we'll write some of these verbose tests here to try to make this really good and have this have really good coverage. And if you want to go back later on and see if you can give it even more coverage and even better tests, please feel free to do so. But let's get started. Let's write some tests. So we're going to start out pretty much the same way we've been starting everything out. We're going to grab our development chains so that we only run our unit tests on a development chain. So we'll do const development chains equals require dot dot slash helper hardhat config. And then we'll say not development chains dot includes network dot name describe dot skip. Otherwise, we'll do describe. So this first describe is going to be our raffle unit tests. And this is going to be an async function. So raffle unit tests so that it comes on the next line and looks a little bit better. All right, great. Now, what are some of the main things that we're going to need to deploy? Well, we're going to need to deploy a raffle. We're probably going to want a VRF coordinator v2 mock created before each. That's going to be an async function where we go ahead and we get these. So we'll say const deployer equals await get named accounts. So we're going to need to import get named accounts or require get named accounts from Hardhat. And then we're going to want to deploy these using our fixtures. So we can say await deployments, and then we're going to import deployments as well from hardhat.fixture, and we're going to call all. We're going to deploy everything. And again, if we look at our O1, our raffle has the all tag, and our OO, our mocks also have the all tag. Okay, perfect. Once we deploy everything, we can say raffle equals await ethers.get contract. And we got to import ethers from Hardhat like so. And we'll say we'll get the raffle contract and we'll connect it to our deployer. And then we're going to do the same thing with VRF coordinator v2 mock equals await ethers.get contract VRF coordinator v2 mock. We'll connect this to deployer as well. All right, great. Our first set of tests describe. They're going to be the constructor. And this is going to be an async function. And let's do this. Let's create an it initializes the raffle correctly. This is going to be an async function. Now, I just want to make a note because ideally we make our tests have just one assert per it. Just keep that in mind is that ideally we want to have just one assert per it, but we're going to have a bunch because, like I said, we're being a little bit loose here. So we want to just make sure that our raffle is initialized correctly. So we'll say const raffle state, and we'll get that raffle state because we want to make sure that we start in an open raffle state. So we'll say const raffle state equals await raffle.get raffle state. And then we want to say assert dot equal. Oh, and then we need to import assert from chai. So assert equals require chai. Assert dot equal raffle state dot toString, because again, raffle state is going to be a big number. And even though our raffle state is of type raffle state, it'll return a 0 if it's open and a 1 if it's calculating. So this gets transformed just into a uint256. When we call it like this, our raffle state variable here will be a big number. So we want to just stringify it. So assert.equal raffle state.toString 0. We'll also make sure our interval gets set correctly. So we'll do const interval equals await raffle dot get interval. And I don't know if we have one of those. Let's actually see interval. See if we have one of those. Oh, we don't have a get interval. Let's go ahead and add a get interval function. So we'll do function get interval. Will be a public view returns uint256 return I underscore interval. We'll have get interval. We'll say raffle.get interval. And we'll also say assert.equal interval.toString. This should equal whatever is in our helper config, right? Because we're using the interval in the helper config. So we say interval.toString should equal, so we'll import that as well, network config, and we'll say the interval should equal network config of, and let's also get our chain ID up here. Chain ID, say const chain ID equals network.config.chain ID, network config of the chain ID of interval. All right, cool. So let's test this so far. HH test or yarn hardhat test. And cool, it looks like it passed and we have our little gas output here. Awesome. Let's go to our hardhat config just so that it doesn't always print out that gas bit there for now. So I'm going to copy paste the gas reporter section from our last project like so, and we're going to have enabled gas be false for now. So now if we run a hardhat test again, we shouldn't have that gas bit printed out. We should just see the tests and perfect. That's what we see. And our constructor test passes. Yay. What's next? Got our constructor, and we probably could have written more tests for the rest of these, but let's just move on. All right, enter raffle. That's going to be our next describe block. So we'll do describe, enter raffle, and this is going to be an async function. And we'll say it reverts when you don't pay enough, right? Because one of the first things that we check is that they're paying enough. So we want to make sure that this actually reverts if they don't pay enough. So this will be an async function where we're going to do that same expect await thing. So we're going to import expect from chai, which comes from those waffle matchers. And we're going to say await expect raffle.enter raffle. And we're not going to pass any value here. We're going to expect it to .b reverted with, and if we look here, we want it to be reverted with this raffle not enough ETH entered. So we can put that in quotes, raffle not enough ETH entered. And now we can try this out, make sure that it actually works. HH test --grep, put this in quotes that you don't pay enough. And awesome, we're passing there. What else do we want to test? Well, we want to test that if the raffle isn't open, we also revert. But we'll test that in a little bit as we kind of test the rest of the functionality. We want to see that it records players when they enter. So this will be an async function. And now we'll enter the raffle, but first we're going to need that raffle entrance fee. Let's go ahead and save that at the top. So we'll say let raffle, vref coordinator v2 mock, raffle entrance fee. And in our before each, we'll say raffle entrance fee equals await ethers dot get entrance fee. This should be raffle dot get entrance fee. So now we have this raffle entrance fee. We can use it to enter the raffle. We'll say await raffle dot enter raffle with a value of raffle entrance fee. And we can make sure that our deployer here has been correctly recorded. So since right now we're connected to the deployer, we'll just make sure that that deployer actually is in our contract. So we'll say const player from contract equals await raffle.getPlayer of 0, because we record them in our players array, and we have our getPlayers function, which pulls them out. And then we'll say assert.equal player from contract should be the deployer. So now we can grep for this in our hardhat test, make sure this works. HH test --grep. Deployer is not defined. We got it up here, but we actually didn't save it globally. So we got to do let, comma deployer, and we'll say deployer equals await get named accounts, and we'll wrap it like this to get the deployer. Awesome. Let's try this again. And awesome. What else should this do? Well, it's also emitting an event. So let's make sure it emits an event. So we'll say it emits event on enter. And this will be an async function as well. And this will be the first time that we're testing to make sure a function emits an event. And the syntax is going to look really similar to what we test for when we check to see if an error is fired. So we're going to say await expect raffle.enter raffle with value of raffle entrance fee .to.emit, and this .to.emit we get from Ethereum Waffle, these chai matchers for emitting events. We can do await expect to emit, and then the event that we're expecting to emit. So we're saying to emit the raffle contract to emit a raffle enter event. And we can copy this, try to test this in our terminal. So we'll say hardhat test dash dash grep, put this in quotes, and that passes as well. Great. Let's now go ahead and test to make sure that we can't enter the raffle whenever this raffle is not open or it's calculating. So we'll say it doesn't allow entrance when raffle is calculating. And this will be an async function. And first we'll enter, we'll say await raffle dot enter raffle. Value is raffle entrance fee. Now what we want to do, we want to get this raffle into a closed state. So we want to get it out of its open state. Well, how do we move this raffle from raffle.open to raffle.closed? In perform upkeep, we move the raffle from raffle.open to raffle.calculating. But perform upkeep can only be called if check upkeep returns true. Otherwise, it'll revert with raffle upkeep not needed. So what we need to do is we need to make check upkeep return true, and we will pretend to be the Chainlink Keeper network to keep calling check upkeep, waiting for it to be true. And once we make it true, then we'll pretend to be the Chainlink Keepers and call perform upkeep to put this contract in a state of calculating. Now, how do we actually do that? Well, in order for check upkeep to be true, we first need to see that we are indeed open, which we are. The next thing that we need to do, though, is we need to do this time passed bit. We need to actually wait that 30 seconds for time to pass. Now, that kind of sounds awful. Do we have to wait 30 seconds for all of our tests? What if our interval was 10 days? Would we have to wait 10 days to run our tests? That sounds ridiculous. Well, Hardhat actually comes built in with a ton of functions for us to manipulate our blockchain to do literally whatever we want it to do. In the Hardhat documentation, there's a section called Hardhat Network Reference inside the Hardhat Network section. And in here, there's a ton of information about how the Hardhat network actually works and different configs that we can do with it. If we scroll down low enough, we can see the JSON RPC methods that we can use on this blockchain. We can do ETH accounts, block number, call, chain ID. We can do all these RPC methods that a normal blockchain has. Additionally, we can do even more than that. We can use these things called Hardhat network methods. Since this is our local Hardhat network and we're using this for testing, we want to be able to test any scenario. And it's these methods that give us the ability to do that. You can go through this and play around and see all the different things you can do. One of them in particular is going to be set storage at, where you can set storage at any place, which is really fun. But some of the special testing debugging methods are going to be EVM increase time and EVM mine. Increase time allows us to automatically increase the time of our blockchain, and EVM mine allows us to mine or create new blocks. Because if we increase the time, it doesn't do anything unless there's a new block mined. So what we can do is we can run await network, and we'll import network from Hardhat, network, await network dot provider dot send EVM increase time, comma, we can send a list of parameters to send with it, which for us are just going to be our interval dot toNumber. And then we'll do +1. Now, right now, our interval isn't stored globally, so we're probably going to want to do that. So let's go ahead and do interval. And then in our before each, we'll do interval equals await raffle.get interval. I'm just going to copy this and we're going to delete this whole line. Wait, raffle.get interval. Since now we're just going to call it interval at a global level, since we're going to use it a lot. Now we're going to say interval.toNumber +1. So we want to increase the time by whatever our interval is to make sure that we can actually get that check upkeep to return true. So additionally, we're going to want to do await network.provider.send EVM mine with an empty array, just because we just want to mine it one extra block. You can also do network.provider.request with an await here. These two would be basically the same, but this one's a little quicker to write. So we've increased the time of our blockchain. We've mined a block to move forward. It should be open. Time has passed. Do we have a player? We do indeed, because we've entered the raffle. We should have a balance because we've entered the raffle. Check upkeep should now return true. So we should be able to call perform upkeep and pretend to be a Chainlink Keeper. So we're going to pretend to be a Chainlink Keeper and call await raffle.perform upkeep. And we're going to pass this some empty call data just by passing a blank array like that. And now this should be in a calculating state. So now that it's in a calculating state, we can say our enter raffle reverts correctly if the raffle isn't open. So now we'll say await expect raffle.enter raffle, and we'll send it value of raffle entrance fee. We're expecting this .to.b.reverted with that raffle __ not open error. Okay, let's try just this in our tests now. So we'll run hardhat test -- grep, put this in quotes, and perfect, that passes as well. Now if we run hardhat test, let's just test everything together right now. And everything is passing. Oh, this is wonderful. Awesome. Let's keep it going. And if we run hardhat coverage, we'll see our coverage is bumping up. We are already drastically better than where we were before. Let's keep going. Well, let's go ahead and test our check upkeep now. So we'll do describe check upkeep. And this will be an async function where we'll say it returns false if people haven't sent any ETH. This will be an async function. So we'll have everything in here be true except for the fact that nobody's entered yet. So we'll do await network.provider.send EVM increase time, comma, interval dot to number +1. We'll do await network.provider.send EVM mine, no parameters. And now we're going to call check upkeep. Now here's the thing. Check upkeep is a public function. So if we just run await raffle.checkupkeep and we pass nothing in, this is going to kick off a transaction because Hardhat knows, oh, okay, it's a public function. They're clearly trying to send a transaction here. If this was a public view function, it wouldn't. It would return that view. But the thing is, I don't really want to send a transaction, but I want to simulate sending this transaction and seeing what this upkeep needed would return. Well, I can actually get that by using something called call static. I can simulate calling this transaction and seeing what it will respond. So instead of raffle.checkupkeep, I can do raffle.callstatic.checkupkeep, and this will give me the return of upkeep needed and the bytes perform data. I can extrapolate just the upkeep needed out of this return by writing const upkeep needed equals this. And then I can do assert not upkeep needed, because right now upkeep needed should return false. So we'll say assert not false, which is true. And if upkeep needed was true, then this would be false and this would break. So that's what we want to do. So let's go ahead. We'll run this, see if it worked. Hardhat test -- grep. And we're in passing. We are in business. Awesome. So this is working perfectly. Well, let's also test that it returns false if raffle isn't open. This will be an async function. And we'll do everything except, and we'll do everything in here, but we'll make the raffle in the calculating state. So we'll do await raffle.enter raffle value raffle entrance fee await network.provider.send, and I'm just going to copy these two lines here because we're going to go ahead and do those. We're also going to do await raffle.perform upkeep. Oh, and another way to send a blank bytes object is to do a string like 0x. Hardhat is smart enough to know that this should be transformed into just kind of a blank bytes object. So either one of these should work. Now we'll do const raffle state equals await raffle.get raffle state, and we'll get upkeep needed. So we'll say const upkeep needed. We'll do exactly what we did above. Raffle.call static.check upkeep. Let's say, excuse me, await raffle.callStatic. Now we can do assert.equal. We'll say raffle state is going to be, or excuse me, raffle state dot to string is going to be calculating, and assert.equal upkeep needed is going to be false. Let's run a grep on that. And perfect. That's also working correctly. Great. Now I'm going to skip over these next two tests because we haven't really learned anything from them. So I'm just going to copy paste them from the GitHub. We're going to return false if enough time hasn't passed, and we're going to return true if enough time has passed. We have players ETH and is open. So we're just asserting true down here, and we're asserting not true up here. If you want to pause the video and copy paste these and write these out, you absolutely can. Copy paste them from the GitHub repo, you absolutely can. Like I said, going through this and making yourself write these and making yourself understand these tests is going to make you a substantially better coder. And let's just test that it all looks good with HH test. Now, as I was recording this, I just realized that for all of our describe blocks, I've been making them async functions. Describe blocks actually don't realize and can't recognize and can't work with promises. So having them be async actually doesn't do anything. So in your describe block, we want to get rid of the async word because it's actually not helping us at all. In fact, it's just extra word and it looks kind of gross. So in all of our describe blocks, we're going to get rid of that async keyword and just have them be functions. Of course, all of our its, though, are going to be using asynchronous functions, which is what we want. So we've written some tests for check upkeep. Now let's go ahead to perform upkeep. Let's create a new describe block. Describe for perform upkeep. This is going to be a regular function. And in here, we're going to start and say it can only run if check upkeep is true. And this will be an async function because we only want perform upkeep to work if check upkeep is indeed true. So we'll say await raffle.enter raffle. We'll send it some value, raffle entrance fee. Oops, sorry, those should be curly braces instead. Then we'll do await network.provider.send EVM increase time interval.toNumber +1 await network.provider.send EVM mine, an empty array there too. The reason that we're moving time forward and moving our block forward, of course, is going to be the same thing as above. We want our check upkeep to return true. And then we're going to say const tx or transaction equals await raffle.perform upkeep. We can either do a blank array or we could do 0x, doesn't matter. And we can assert tx. Now, if tx doesn't work or this errors out or something, this will fail, right? So that's how we know that this actually can work. So let's test this out. We want this only to work if check upkeep is true, and we made check upkeep true by all the stuff that we did above. So now we'll do yarn hardhat test -- grep with our it block here. And I spelled perform upkeep wrong. Perform upkeep. Let's try spelling things correctly. And let's run that test again. And great, that's working. All right, well, what else do we want to do? We want it to revert with raffle upkeep not needed if check upkeep is false. So in here, we're going to say it reverts when check upkeep is false. This will be an async function. And we're going to do that same syntax, await expect raffle.perform upkeep empty bytes object .to.b reverted with, and what do we want it to be reverted with? We're hoping it's reverted with this, with that. We can run this test here, hardhat test -- grep, paste that in, and we see that is indeed passing. Now, something that you'll notice here is that our revert actually goes ahead and reverts with all this extra stuff as well. Our test is smart enough to know that if all we do is put the name of the error that is getting reverted with, then it's good enough. If we want to be super specific, we can actually go ahead and make this a string interpolation and add all of these in here. So we can add the balance that we expect, we can add the players that we expect, and we can add the raffle state. For now, we're just going to keep it as we're expecting this. But if you want to be super specific, you can have your tests expect for exactly the specific values that you're looking for. But all right, what is the last thing we should expect for? Well, we should check to see that this actually gets called, the raffle state gets changed, and we emit this event. So let's go ahead and add that. We'll say it updates the raffle state, emits an event, and calls the VRF coordinator. This will be an async function as well. Let's do this. So let's go ahead and let's make check upkeep true. I'm just going to copy paste these first 3 lines since it's going to be exactly the same. We're going to enter the raffle. We're going to increase the time. We're going to mine a new block. Then we're going to call perform upkeep. So we're going to say const tx response equals await raffle.perform upkeep with an empty bytes object. Then we're going to do const tx receipt equals await tx response dot wait for 1 block. From this receipt, we're going to get the request ID. We're going to say const request ID equals, we can get the request ID from this emitted event. However, we should look at our VRF coordinator mock again. When we call request random words, both in the mock and then in the actual contract, you'll notice that it also emits an event with random words requested. And if you look in here, the second parameter that it has is indeed the request ID. So in reality, us emitting the request ID is redundant. We can just use the emitted request ID from the VRF coordinator. For the purpose of this course and showing you what an event looks like, we're going to leave it in there. But if you want to go back and refactor this, you would definitely want to remove this emit. But for this test, let's do tx receipt dot events. And this is going to be the first event instead of the 0th event, because before this event gets emitted, this function is going to emit an event. So instead of the 0th event, this is the first event that gets emitted after this one. So tx receipts.events of 1.args.request.id. And then we're going to say assert request ID.toNumber is greater than 0. And then we'll also assert that the raffle state equals 1. So we're going to do const raffle state equals await raffle.get raffle state. And this should actually be raffle state dot to number or to string, and then, do whatever we want to do. And this is a very big it, but we're going to copy the whole thing anyways. test -- grep, paste that in there. Rerun it, dot to string equals 1. Try this one more time, and perfect. We are passing. Great. Now it's time for fulfill random words. And this is where we're going to learn a lot of fantastic stuff here. So we're going to make a new describe block. I zoomed out a little bit here. And this is going to be our fulfill random words. This is going to be a function, of course. And in here, we're actually going to add another before each. We want to have somebody have entered the raffle before we run any tests in here. So we're going to do a before each, which will be an async function. And we're just going to run await raffle.enter raffle with a value of raffle entrance fee. And then we're going to do await network.provider.send EVM increase time of interval dot to number +1, and then await network.provider.send EVM mine, comma. Before we try to do any testing of our fulfill random words, we're going to have somebody enter the lottery, and we're going to have increased the time and mined a new block. Okay, cool. So the first thing we want to do is we want to see that fulfill random words can only be called so long as there's a request in flight. So long as there's a request ID, so long as request random words has been called. So we can actually check that by running it can only be called after perform, and this will be an async function. And in here, we're going to revert on some requests that don't exist. So we'll do await expect VRF coordinator v2 mock dot fulfill random words. And if we look at our VRF coordinator v2 mock, in here has the fulfill random words function, which is what the Chainlink node actually calls. And inside this function in the actual contract calls another contract that does the random number verification. So we're basically checking this part right here. If the request doesn't exist, we're going to get this non-existent request here. And as you can see, it needs a request ID and a consumer address. So we're going to guess 0, and the consumer address is, of course, is going to be raffle.address. We're going to expect this to.b.reverted with non-existent request. And then we're going to do this exact same thing with a different request ID, a request ID of 1. And hopefully we're also going to get non-existent request. Now, ideally, no request here would ever allow this fulfill random words to go through. Now, it obviously would be really hard for us to test every single possible request ID. We're going to see a way in the future to actually test for a ton of these variables with something called fuzz testing, but we'll get to that in the future. And I spelled describe wrong, so let's actually spell describe correctly. Go ahead and run this, hhtest-grep, and great, it passed. Now I'm gonna make just one more test here that's gonna be way too big. But all right, now the test that we're about to write is gonna be a really big test. And we'd probably wanna split it up into different sections, but I actually figured that this was actually the best way to show this section. And it's gonna be exactly what we're gonna do when we get to our staging test. We're gonna write this test literally almost exactly the same. So let's write it. This is basically gonna be the test that puts everything together. So we're gonna test that this indeed picks a winner, resets the lottery, and sends money, which is kind of a lot for a single it. We probably would wanna split those into their own pieces, but for this, we're just gonna put them all into one. This is gonna be an async function. Now, we are going to learn a couple of new tricks here, so definitely be sure to follow along. Now, for this one, we're also going to add in some additional entrances, additional people who are entering this lottery. So we'll say const additional entrance equals 3. We're going to have some more of those fake accounts from ethers enter our lottery here. So we're going to say const starting account index equals 2. Since deployer equals 0, equals 1, since deployer is 0. So we're going to have new accounts start from index 1. And we're going to do a little for loop for let I equals starting account index. I is less than the starting account index plus additional entrance I plus plus. We're going to do a little loop and connect our raffle contract to these new accounts, and then we're going to have these new accounts enter our raffle. Const account connected raffle equals raffle.connect accounts of I. And do we have accounts defined somewhere? We don't, so let's get accounts defined somewhere. We'll say const accounts equals await ethers.get signers. And then we're going to do await account connected raffle dot enter raffle with the value, of course, of raffle entrance fee. We're going to connect 3 additional entrants to our raffle. So we're going to have a total of 4 people connect into this raffle. Now that we have them in here, we're going to keep note of our starting timestamp. So we do const starting timestamp equals await raffle dot get last timestamp. And here's where we're going to get a little bit tricky. What we want to do is a couple of things. We want to perform upkeep, which is going to mock being chain link keepers, which will kick off the chain link, which will kick off calling fulfill random words. And we're going to mock doing that as well, mock being the chain link BRF. Once we do that, we can, of course, just check to see, okay, did the recent winner get recorded? Did the raffle get reset? Does players reset? Is the timestamp reset? Is everything reset? But we want to do this in a specific way. If we're doing this on a testnet after we call fulfill random words, we will have to wait for the fulfill random words to be called. Now, since we're working with a Hardhat local chain, we don't really need to wait for anything, right? Because we can just say, okay, boom, snap our fingers and adjust our blockchain to do whatever we want. But we're going to simulate that we do need to wait for that event to be called. So in order for us to simulate waiting for that event, we once again need to set up a listener. Now, if we set up a listener, we don't want this test to finish before the listener is done listening. So we need to once again create a new promise. And this is going to be incredibly important, especially for our staging tests. So we're going to do await new promise. And this is going to be exactly the same as we set it up before. It's going to be an async function that's going to take resolve and reject as parameters. And we're going to use this little arrow syntax here saying this is an async function, basically. And we're going to set up once again that once syntax. We're going to say raffle.once. What's the event name? Winner picked. So we're going to say listen for this winner picked event. We're going to say raffle.once winner picked happens. Do some stuff. Again, this is just an anonymous function. So we're going to say raffle.once the winner picked event gets emitted. Do some stuff. So we're setting this up. Now it's in this function, we're going to add all of our asserts and everything because we want to wait for winner to get picked. Now, before the event gets fired though, we of course need to actually perform and call fulfill random words. So this is going to seem like it's a little bit backwards, but that's because we want to set up our listener so that when we do fire the methods that will fire the event, our listener is activated and is waiting for it. So we're going to put all of our code inside of this promise now, because if we put it outside of the promise, we put all the code outside of the promise, this promise will never get resolved because the listener will never fire its event. So if down here, we call fulfill random words with something, which the spelling is bad, but let's say we called it down here, this piece of code will never reach this fulfill random words because it's always going to be waiting for this once to get resolved. So we need to add all of our code inside the promise, but outside this raffle.once. Now, we don't want to wait forever, right? Maybe there is an issue here, and we want to be able to reject this if there's an issue. Now, what we can do is in our hardhat.config, we can add a timeout. So we can add this mocha section, and we can give ourselves a timeout of 200,000 milliseconds, which is going to be 200 seconds max. If this event doesn't get fired in 200 seconds, this will be considered a failure and this test will fail, which is what we want. And I typically like to just wrap this in a try catch because if something fails, it'll cause you a whole bunch of headache. Catch E. And if anything fails, we'll also reject. There's an issue with us calling some function. We'll just say, hey, okay, that's a failure. Boom, you fail. That way our promise can get resolved in a timely manner. We're going to add this code in a little bit, but let's keep going. And the try catch should be in the once above the resolve, because this is the listener. So sorry, we want the try catch to be inside the once. If this takes too long, we want to just go ahead and throw an error. Otherwise, we're going to resolve. Now, outside the listener, but inside of the promise, we're going to do this bit here where we go const tx equals await raffle.perform upkeep, and we'll pass it the empty bytes object. We'll get const tx receipt equals await tx.wait of one block. And then we're going to do await brf coordinator v2 mock dot fulfill random words tx receipt dot events of one dot args dot request id comma raffle dot address. So then the final thing that we're going to do is we're going to get this vrf coordinator v2 mock. We're going to have it call fulfill random words, which takes the request ID and the consumer address. So we're going to mock it, give it the request ID, which we get from the transaction receipt, and the consumer address here. All inside this promise, we're setting up a listener for this winner picked event, and then we're mocking the chainlink keepers, and then we're mocking the chainlink VRF. And once this function gets called, this function should emit a winner picked event. So this raffle that was set up, that was listening for this to get emitted, will pick up and go, okay, I found it. I found the winner picked event. Now we can go ahead and do some stuff. So once the winner picked event gets fired, we'll do a little console.log, found the event like this, and we'll jump into our try catch. And this try catch is going to be basically us doing all these asserts in here. So first we want to say const recent winner equals await raffle.get recent winner. And we're going to be checking just everything in this raffle, right? We're going to be checking that the recent winner is right, that the raffle state's been reset, the players have been reset, players has been reset, etc., etc. So we're going to say const raffle state equals await raffle.get raffle state. We'll say const ending timestamp equals await raffle.get last timestamp. And let's start doing some asserts. So first, we should assert that this splayers array has been reset to 0. So if we call get number of players, it should be 0. So we can do const num players equals await raffle.get number of players, like so. And we can do assert dot equal num players dot toString is going to be 0. What else can we assert? Well, we can assert dot equal the raffle state should be back to being open. So raffle state dot toString should be 0. We should assert that the ending timestamp is now greater than the starting timestamp, because the last timestamp should have been updated. We also want to make sure our recent winner is correct. So we'll do console.log recent winner. Now we could go to the VRF coordinator mock and we could simulate this and try to figure out who the random winner is. Do console.log accounts 2. And then just to show a bunch of them, we'll do 0, 1, and 3. Our raffle.once, this needs to be an async function, not just a regular function. Let's try that one more time. Get latest timestamp is the correct function. So let's update this with the correct latest. Let's put latest in there because I'm spelling some things wrong. I sure am. Looks like we're printing out recent winner here when we haven't even initialized it. So let's move it up and then we'll do console.log recent winner. So I know this is a massive test here, but let's give it a try and see if everything kind of does what we think it should do. And it's slowing down here, which is good because we're doing a lot of stuff. And aha, we finally get this passing thing to come out. And we did a ton of console.logging, so there's a lot of stuff in here. All of these signers are getting printed out, so let's just make this a little easier to read. We'll add .address to all these. We can see who the winner is. So it looks like the winner is going to be account number 1, which is great. So what we can do is, now that we know account number 1 is going to be the winner, we can get that winner's starting balance way down here before we call fulfill random words. So we'll say const winner starting balance equals await accounts 1 dot get balance. So yes, you can just call get balance right like that. And now that we have the winner starting balance back in our tests, we can say const winner ending balance equals await accounts 1 dot get balance. And we can make sure that this winner got paid what they need. So now we're going to do a big assert with some money stuff. Just trust me, this is what the math is. So we're going to do assert dot equal winner balance dot toString, winner ending balance dot toString should equal the winner starting balance dot add the raffle entrance fee dot multiplied by the additional entrance dot add the raffle entrance fee that we paid dot toString. So this math is basically saying the winner should end with a balance of all of the money that everybody else added to this contract. And that's it. So we can run this test one more time. And gosh darn it, it passed. Okay, so there was a lot of code here. And this might have been one of the hardest pieces of this entire course, is going to be this part right here. So if you struggled a little bit with this, don't let that bog you down. This is probably one of the more difficult sections of this course. Let's do a quick refresher of just this test that we're doing, and then we'll see it in action when we do it in our staging test. What we did is we're picking a winner, resetting the lottery, and we're sending money. Basically what we're doing is we're testing that this fulfill random words thing does what we want it to do. A random winner wins and they get the money. So how do we actually do that? Well, we first started off by having a bunch of random people enter the lottery. Great, sounds good. Now, what we wanted to do was we want to call perform upkeep and fulfill random words. We want to pretend that the random number was drawn. And that's what this code down here does, is it calls that random number. And what we could have done was we could have had all these assert and checked all the variables after we did this, right? We could have totally done that. However, on a test net where we don't always know exactly when a transaction is going to finish, we have to wait. We have to listen for an event to be fired. Before we could call the transactions that would end this whole thing, we needed to set something up to listen for that event to be fired. And we said, hey, only once this event is fired, only once this transaction is called, can we do our testing. Now, for our local network, we are mocking the VRF coordinator. So we have control. We know exactly when this is going to run. But on a testnet, we don't. So you'll see in our staging tests, we won't have any of this here, and we'll have to rely on setting up a listener to listen for the Chainlink VRF and the keepers to fire their events. And that's why the staging test is going to be so important to make sure that we're doing everything correct. And that's why we set up our local tests like this so that it mimics what we're going to be doing on our staging test, what we're going to be doing on a real network here. And again, we're setting up this listener and we're saying, once we do hear this event, then we're going to try to actually check all of the balances and check that everything is working as intended. And if we don't see it, we're going to reject. And if there's a timeout, if it takes more than 200 seconds, we're going to say, okay, something went wrong. We're going to cancel it. And actually, I'm going to bump this up to 300 seconds because I think 200 seconds is not going to be enough. And depending on how quick the Rinkeby testnet is, you might have to bump this up even bigger. So just keep that in mind. But okay, we have just built some fantastic tests. Let's go ahead and let's just run HH test to see if all of our tests are going to pass. And wow, 14 passing, everything is passing here. We are looking good. This is fantastic. All right, so now that we have our unit test, let's go ahead and create a staging test. Our staging test is going to look really similar to that massive test that we just created down here. And the reason we set up our unit test to do this await promise thing with the raffle.once was because this is actually how we're going to need to wait on a testnet or a mainnet for a winner to be picked. We cannot, on an actual testnet, pretend to be the Chainlink VRF. We can pretend to be the Chainlink Keepers if we want, but we're not going to make sure that the Chainlink Keepers is actually working. But we are going to be doing this because we want to listen for that event to be fired. We want to listen for the Chainlink VRF to respond with the winner. So let's create a staging test. And this is a test that we're going to run on an actual testnet here. Okay. So we're going to create a new test called raffle.staging.test.js. And this is where we're going to put our staging test. Now, we can actually code this pretty quickly because most of our staging test is going to look real similar to our raffle test here. So for now, let's just grab this whole first part and then we'll adjust it as we need. And then we'll close it off because we're definitely going to need a raffle. We're not going to need a VRF coordinator mock because, again, we're not going to be using a mock since we're on an actual testnet. We will need the raffle entrance fee. We will need a deployer. We will need a deployer, and we might need the interval, but let's delete it for now. We probably won't need the chain ID, so let's delete that as well. Awesome. Something that we want to keep in mind is that when it comes to our staging tests, we only want our staging test to run when we're on a testnet. We don't need to run our unit tests because our unit tests aren't checking that compatibility with a testnet. We want our unit tests to only run on a local network, and we want our staging tests to only run on a test network. This is where, again, in our tests, we're going to check to make sure what type of chain we're on. And oops, it looks like I already imported the development chains here. So we're actually, in our staging tests, we're going to check before we run any test what kind of network we're on. So we're going to say if our development chains dot includes network.name. We're going to say if our development chains includes network.name. So if the chain we're on is in the development chains, and again, we're going to use this ternary operator where we say if we are on a development chain, do something, and then if we're not on a development chain, do something else. If we are on a development chain, what are we going to do? Well, we want to skip this. And we can actually skip this by putting in this describe.skip. And this will skip this whole section here. And then we can say, if we are on a development chain, go ahead and do our thing. So this is some really nice syntax that allows us to skip our staging tests if we're on a local network. And additionally, we can grab this syntax, go into our raffle.test.js where we have our unit tests and add the bang operator, which is the not, and hit save. And now we're saying, if we're not on a development chain, skip it and only run this if we are on a development chain. So this says run this only on a testnet or a mainnet. And then this says run this only on a local network. So great. So we have a deployer, which we're going to need. We are not going to need to deploy any fixtures because we're going to run our deploy script and our contracts should already be deployed. We will need a raffle. We won't need a VRF coordinator mock, so we can delete that. We will need the entrance fee, and we probably won't need the interval, so we can go ahead and delete that too. All right, awesome. So we have our describe, we have our before each. Let's make our tests. And I'm just gonna make one giant test to test kind of everything end to end. And you can add more tests later on yourself if you want to. Our staging test is gonna be really similar to this massive test that we made down here. And in fact, we're gonna use most of this code here as our boilerplate. So let's create a describe, and we'll say, and we'll actually just copy this describe, fulfill random words, and paste it in here. Because again, we're going to be using a lot of the same code in our staging test here. Great. So now we'll say it works with live, chainlink keepers, and chainlink VRF. We get a random winner, async function, boom. So this is going to be our test in here. So in this test, we want to enter the raffle, and we shouldn't have to do anything else except for enter this raffle, because the chainlink keepers and the chainlink VRF are going to be the ones to actually kick off this lottery for us. We'll do a quick grabbing of the starting timestamp to have it before all of this kicks off. So we'll say const starting timestamp equals await raffle.get get latest timestamp, get latest timestamp. We're going to grab this because later on we're going to test to see if the timestamp has indeed moved forward. We want to enter the lottery, right? We want to run the command we've been running over here all the time. We want to do, await raffle.enter raffle, but we don't want to call it yet, because same as what we did over here, we want to set up our listener first. Now, in here, we probably should have set up our listener before we entered the raffle. However, we controlled the blockchain, so putting it in that order was okay. But we want to set up the listener before we enter the raffle, just in case the blockchain moves really fast. And we're going to set up the listener the exact same way we did it over here. So we're going to say await new promise. And this is going to be an async function that takes a resolve and a reject. And we're going to use a little arrow notation here. And in here, we're going to set up the listener. We're going to say raffle.once. Once that winner is picked, we're going to do another async function using that arrow function syntax. We'll say console.log winner picked event fired. And only once we get this winner picked can we start doing our asserts in here. Can we start making sure that there's a winner, there's a verifiably random winner, it's been picked, the money's been moved, etc. This is where we'll do our try catch. And if there's any error, we're just going to automatically reject. We're going to reject the promise. And if all goes well, of course, we're going to resolve the promise. So our listener has been set up here. We haven't added our asserts here, but we will. Let's just go ahead and write the rest of the test, and then we'll go back and we'll update this listener. So our listener has been added. And inside here is actually where we're going to enter the raffle. So inside here, await raffle.enter raffle value is going to be raffle entrance fee. And really that's it, right? So we're setting up the listener, then entering the raffle, and this code won't complete until our listener has finished listening. Because again, this whole sec is in and await. So we're gonna say, okay, cool, set up the listener, wait for this to finish. And then when it gets here, it goes, okay, this is the end of the code. Are we all done executing? Oh, no. Resolve or reject hasn't been called yet. And that's because we're still waiting for the listener to finish listening. Now, once we get this winner picked event emitted in here, we're going to get that recent winner. So we'll say const recent winner equals await raffle.get recent winner. We'll get the raffle state. We'll say const raffle state equals await raffle.get raffle state. We'll get the winner's balance. So we'll say const winner balance equals await recent winner. And since we're only entering with our deployer, we should check to see the deployer's balance at the end. And we can't do it right with this deployer object here. So we'll have to do deployer account equals await ethers.get signers. And we'll wrap this actually we'll just say this is accounts here like that. And then we'll just do accounts of 0 because accounts of 0 is going to be our deployer. So our winner balance is going to be accounts of 0 dot get balance. And then we're going to do const ending timestamp equals await raffle dot get latest timestamp. And we should also get the starting balance. So we'll say winner ending balance. We should also get the starting balance right after we enter. So we'll say const winner starting balance equals await accounts 0.get balance. So that now we can do some comparisons. All right, great. Let's do the comparisons now. So we should first expect the raffle to be reset. So we can do this a few different ways. Down here, we did number of players. We could also say await expect raffle.getPlayer 0.2.b.reverted, right? Because get player of 0 should get reverted because there's not even going to be an object at 0. So that's another way we can check to see if our players array has been reset. Next, we can do assert.equal recent winner .toString. This should equal our account 0.address, aka our deployer. What else can we do? We will assert.equal raffle state to 0. We want this enum to go back to open after we're done. And then we finally want to make sure that the money has been transferred correctly. So we'll do assert.equal. This should be winner ending balance .toString should be equal to winner starting balance .add raffle entrance fee .toString. So if we look down here, they enter the raffle. We check their starting balance right after they enter, and they basically should just get that raffle entrance fee back, right? Because they're the only ones who have entered this raffle. And then we can do one more assert. We'll do assert that the ending timestamp is greater than the starting timestamp. And then we'll, of course, say resolve. So if this all goes well, we resolve. If there's an issue with any of these asserts, we're going to catch those errors and we're going to reject. And this is going to be false. And this whole test is going to go, there was an issue. We now have a staging test that looks really good here. Let's try this out. Let's try our staging test out from start to finish. So now, in order for us to test this staging test from end to end, we're first going to need to get our sub ID for the Chainlink VRF. Then we're going to need to deploy our contract using the sub ID. We're going to need to register the contract with Chainlink VRF and its sub ID. We're going to then need to register it with Chainlink Keepers. And then, of course, we're going to run the staging tests. So let's do it. So first thing we're going to need to do is what? Get our sub ID for Chainlink VRF. Okay, great. So we're going to come over to vrf.chain.link. And we're going to need to create a new subscription. If we don't have enough RinkB ETH, we want to head over to the full blockchain solidity course. Here, we're going to scroll down and we're going to look for the recommended testnet here, which is RinkB. And we're going to use the faucets link to get some RinkB link. We're on faucets.chain.link. Let's switch over from Coven to Ethereum RinkB. We know we're going to need some link and some ETH. So let's just go ahead and get both. All right, great. Now that our transaction has gone through, let's just double check our wallet here. And it looks like we do indeed have Ethereum here. And if you don't see the link, you can head over to Link Token Contracts. Link Token Contracts in the Chainlink documentation. We'll scroll down to RinkB. We'll grab this contract address, import tokens, and we'll paste it in here. Add custom tokens, import tokens. Great. Now I can see my ETH and my link here. Perfect. We have some ETH. We have some link. Let's head over to VRF Subscription Management, and we're going to create a new subscription. Again, we could totally do this programmatically because the user interface here is only helping us facilitate call contracts to the registration contract that's completely decentralized and on-chain. So let's go ahead, create subscription. We'll create subscription. We'll confirm the transaction to MetaMask on the RinkB network. We'll do a little bit of waiting. And great, once it's gone through, you can go ahead and click the Add Funds button. I'm going to show you what it looks like if you accidentally refresh and jump off though. So if you refresh, and you go back to vrf.chain.link, you should have a new active subscription. And you'll see this number here. If you click on it, this is your subscription ID. Great. So we can actually take this, come back to our code into our helper Hardhat config, and we can paste our subscription ID under subscription ID for our RinkB network here. Awesome. Now that we have a subscription, we can see it's not funded with any link. So we don't have any Oracle gas here. And we don't have any consumers. right? Our consumer is going to be our raffle or our lottery contract. So let's add some funds first. And we don't need to add a whole lot because we're only going to be testing once. So let's just go ahead and add 2 link here. This number might change depending on different costs of the test nets and how much link token there's available. So if you're actually working on a main net, be sure to head over to docs.chain.link, EVM chains, contract addresses. You can read more about the costs of some of these different chains so you can figure out exactly how much to put in here. And if you go to the full blockchain solidity course JS, we can scroll down to lesson 9. There's a recommended link amounts for Ringbeat staging tests. For Chainlink VRF, for now, we're going to put 2. For Keepers, we're going to put 8. But feel free to refer to here so you know how much to put in. So let's go ahead and confirm. We're going to approve adding funds here. We'll go ahead and confirm. And we're now funding our subscription so we can pay that Oracle gas to get our random numbers. Great, once we're funded, we can close it. We'll do a little refresh and we can see the balance is now 2 link when we don't have any consumers. Perfect, so we've got our sub ID, we've funded it. Now let's go ahead and deploy our contract. And we already know that we should be all good for deploying our contract. We go to our .env, we'll need to add all of those same parameters from our previous projects. We'll need a Ringbeat RPC URL. We'll need our private key. If we want to verify, we'll need our Etherscan API key. And if we want to do a gas output, we'll need our CoinMarketCap API key. So let's make sure we have all that. And we'll look at our deploy script once again, just real quick. We'll look at our helper Hardhat config just real quick. And it looks like we do indeed have everything in here. And we should just be able to deploy it in one command. So we should be able to do yarn Hardhat or just HH again, deploy -- network Rinkeby. Let's go try this out. All right, it looks like we've compiled successfully, we've deployed it successfully, and we've even verified it. We can go and open it up on Ringbeat Etherscan, and we can see our code here has been verified. Oh, and it's looking beautiful. We can read from it, which is great. We can see all these commands here now that it's verified. And if we look at the get raffle state, we should indeed see that it's open, right? And it's going to stay open until somebody ends the raffle and updates the amount of ETH that the contract actually has. Now that we've deployed our contract using that sub ID, we need to register the contract with Chainlink VRF and with Chainlink Keepers. So we need to add this consumer to tell Chainlink VRF, hey, this is the contract that you're looking for now. So we're going to go back to vrf.chain.link and we're going to grab this contract address and we're going to add it as a consumer. Your subscription is ready. You can now add consumers. We're going to add consumer. And again, this website is just here to help facilitate us interacting with the contract. So we're going to approve add user. We'll go ahead and confirm, and the transaction is going through. While we wait for this to go through, we can go to keepers.chain.link and do the same thing. Work with the user interface to register a new upkeep. So we'll go ahead and add our email, hardhatfreecodecamp@gmail.com. We'll call this raffle upkeep. We'll paste our upkeep address in here. We have our admin address, and you can ignore this bit right here. For gas limit, this is going to be the gas limit of the perform upkeep function. If we did our gas estimator, we could just check to see how much that perform upkeep costs. But for now, I'm just going to put 500,000. That's probably overkill, but that's fine. Check data, we're going to keep blank because again, our check upkeep doesn't take anything. And then starting balance, we're going to put as 8. And if you forget to put a starting balance here, you can always fund it later. So let's go ahead and hit register. We're going to get a MetaMask pop-up. We're going to go ahead and hit confirm, and we can go back to our VRF and see that it's indeed been added. And awesome, we now have a consumer on our VRF. So now let's just wait for our keepers to go through. Upkeep registration request submitted successfully. On a mainnet, you might actually have to wait a little bit for your request to go through, but on a testnet, it should automatically go through. Now, if we go back to keepers.chain.link, we should now see, if we scroll down to my upkeeps, we have a raffle upkeep here. And I have 2 because I accidentally used the same account that I tested on. You can ignore the 2, you'll have 1. But this is the one that we just created. And we can actually see what our balance is and then what the minimum balance for this actually is. So it looks like 8 link was a little bit too low. So let's go back to faucets.chain.link/rinkby. Now that we have some more link, we can come back to our raffle upkeep and we can go ahead and hit add funds. And we'll add just 3. And we'll go ahead and confirm. We first need to give permission to spend. We approved our link transfer. Now let's actually transfer the link to the contract. And all right, funds added successfully. So now let's do a little refresh. Now we no longer see that message saying that it's underfunded and we have our balance, and we can see that it's more than the minimum balance. We can see the history that we just funded this twice. Once this actually kicks off, we'll see activity type will be like perform upkeep or something. We've got our sub ID. We've deployed the contract. We've registered with Chainlink VRF. We've registered it with Chainlink Keepers. Now all we need to do is run the staging test. Now running our staging test is essentially going to be the same as us calling this enter script, right? Because all we're doing in our staging test is entering the lottery, and then we just have a whole bunch of validators that we're running to make sure that things are doing as we expect. Since our contract is actually verified, what we could do on RinkB Etherscan is we could actually go to this write contract section of the contract, and we could even connect our wallets to it. And once this turns from red to green, after a little refresh, we'll now see that it's green, it's connected. We could even call functions on this contract ourselves. So we could enter the raffle ourselves. We would add, however much ETH to enter the raffle, and that would kick off the keepers and the VRF as well. So we could call it via Etherscan. We could obviously call it via our staging tests here. We could call it via our scripts. We could call it via the console. There's a ton of ways to actually do this. But moment of truth here. We're going to run our staging tests, which is going to have us enter the lottery and set up a listener to make sure that everything works correctly. And additionally, we'll see on our raffle upkeep history, we'll see a transaction go through, and then we'll see a transaction on our Chainlink VRF as well. Are you ready? I sure am. Let's do this. So we'll do HH test -- network RinkB. And that should be all we need to do. And in our staging test, we probably should have added some console.logs in here to tell us, what step that we're on with each, but we forgot to. So if you follow along with the repo associated with this, we've added the console.logs in the test there. But all right, if we go to the Etherscan for this contract, we go back to the RinkB Etherscan for this, we paste in that address. The first step that we're doing in this test, of course, we're setting up this listener. The first transaction is going to be entering the raffle. That's going to kick everything off, right? So if we refresh a little bit on Etherscan, we do indeed see we've entered the raffle and we've updated the balance of the raffle. Okay, awesome. So raffle has been entered. Now, then what happens? Well, if the raffle has been entered, if we go to raffle.sol, if it's open, if enough time has passed, if there's players and it has a balance, which we just checked it does, this will get kicked off by the keepers. So if we go to the keepers, and we do a little refresh here, after a little bit, we do indeed see check upkeep passed, and we see a perform upkeep having gone through. Great. What does perform upkeep do? Well, perform upkeep calls the Chainlink VRF. So now if we go over to Chainlink VRF, we do a refresh here, we go down to history, we do indeed see one of the transactions has gone through. We can see the transaction hash, the link spent, etc. And now if we go back to our tests, we do indeed see raffle unit test, fulfill random request, winner pick, event fired. And this means that we just went through this entire process of having a perfectly, truly decentralized raffle work on an actual testnet with our integration test working correctly. Absolutely massive. Huge congratulations if you've made it this far and if you just walked through that integration test with me. Now, balance of our contract has now been reset to 0 because our wallet address just won the lottery, right? And got the money back. Now you might be wondering, hey, I see the create raffle function and I see enter raffle, but I don't see, didn't the Chainlink nodes just call perform upkeep and fulfill random words? How come no matter how often I refresh, I don't see those transactions here? Well, those are actually going to be considered internal transactions. Fulfill random words is actually called through the VRF coordinator, and the VRF coordinator contract then calls fulfill randomness. So we can go to internal transactions, and one of these transactions is going to be the transaction to the VRF coordinator contract, which calls our contract. Same thing with perform upkeep. Perform upkeep, the Chainlink nodes actually call through the registry contract, and then the registry contract calls perform upkeep. That's what we see here. And if we go through the internal transactions, we'll see them there. Now let's look at this enter raffle as well. And since we've learned about events and logs, we can actually go to the log section now, and we can see our log or our event being emitted here. We can see the name, raffle enter. We can see the topic 0, which is going to identify this entire event. And then we also see this number here, which is what? Which is index topic 1, address player. And then there's no data associated with this, right? Because we only have indexed parameters, which again, show up as topics. So this is absolutely phenomenal. Wow, absolutely massive. And we can rerun our unit tests just by test, and this will only run our unit tests. And we can see that these are all passing as well. Things are looking fantastic here. And we have just successfully created a verifiably random, autonomous, decentralized raffle and or lottery deployed on the blockchain. You should be so excited right now. Now, I'm not going to show you how to push this up to GitHub. However, if you want to push this up to GitHub, and again, tweet at me, tweet at Chainlink, tweet at Free Code Camp, please feel free to do so because you just did an amazing job getting this far. And if you're going to want to push this up to GitHub, remember, we're going to want to put a .gitignore in here, where we add a ton of stuff like .vs code, artifacts, cache, deployments, node modules, etc., type chain types, all this stuff. You can find a sample .gitignore, of course, in the GitHub repo associated with this. This is an advanced project. We did a lot of really advanced things here, and this is the section of the course where I think at this point you've got most of the fundamentals down. And now we're going to move into more front end, and we're going to move into more industry specific and more advanced topics that are really going to supercharge you and make you one of the masters of the blockchain and the smart contract realm. So huge congratulations one more time. Definitely go celebrate. Definitely go for that walk. Take a quick break. Let everything we just learned settle in your brain and get ready for the next one. All right, now we're going to go over the TypeScript edition of this lesson. We're going to go a little bit quickly here because we're not learning too much new stuff for this TypeScript edition. So if you want to just follow along, you can open up the repo here and use the TypeScript branch. One thing to note that is a little bit different is when we do our promise in our tests, we're doing await promise void because we're not going to be returning anything with our promise here. But the rest is going to be exactly the same. We're going to have a hardhat.config.typescript that's going to use imports once again. Everything else is pretty much the same. We're going to export the config like we did last time. In our package.json, of course, we're going to have all of our TypeScript dependencies as well. And then our deploy scripts are going to follow that same functionality that we've used before. So now our deploy scripts use a type deploy function on our variables that we export at the bottom. And we also import the Hardhat runtime environment type, where we pull the deployments, get named account, and networks from. In our tests, of course, we're still importing the types of these contracts from type chain/types, like you see here. Like for example, raffle is going to be assigned to raffle. VRF coordinator v2 mock is going to be assigned to type VRF coordinator v2 mock. And if we wanted to deploy with these contract factories, we could as well. So those are going to be the main differences with TypeScript. There's not anything really new there, but again, if you want to follow along with TypeScript and you want to code everything in TypeScript, an example is here for you. All right, welcome back. I hope your break was absolutely fantastic because now we are getting into more advanced full stack / front end development. We've done the back end development. We've created smart contracts. We've created our lottery in our last section. And we have all this wonderful code that allows us to work with our own provably decentralized lottery. In order for regular everyday people to use our lottery, we're going to need to build a front end. Now, previously, we learned to build a front end with raw HTML, JavaScript with our FundMe project. We created a front end with just pure HTML and JavaScript. Just creating applications with HTML and JavaScript is great. And if that's what you want to do, you absolutely can. But doing it with those vanilla protocols has some limitations. And working with a framework like what we're going to be working with in this section is going to make our lives a lot easier. We're going to be able to develop quicker, have more functionality, and do more in less time. As you remember back to that project, it wasn't really a fleshed out project, if you remember. It was just a bunch of buttons, and that was really it. So working with a framework is really going to enable us to put more features and add more styling to our applications really easy. Once again, the code for this entire section is located in our lesson and is located in this GitHub repository associated with the course. Now, I have to put an asterisk here. As I've said many times, the front end sections of this course are not required. we're not going to learn anything new about the backend in this front end section. So if you don't care about building websites, all you want to do is learn the smart contract aspect of this course, you can skip these sections. But if you do want to learn how to build these front end applications, if you do want to give users and non-developers the abilities to interact with our smart contracts, then please continue to watch.